Hello, friend. Tonight, let's talk about something that wasn't real. For 35 years, we believed Neptune was blue, deep blue. The kind of blue that made you think of sapphires pulled from ocean trenches of midnight skies over frozen seas. We had photographs, we had proof, or so we thought. But here's the quiet truth. Neptune was never that color. The blue we loved, the blue we put in textbooks and documentaries and children's books about space. It was beautiful. It was striking. It was wrong. In January 2024, scientists finally showed us what Neptune really looks like, and it changed everything we thought we knew about the edge of our solar system. Before we drift into this story, if you find comfort in these quiet journeys through science, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more stories, told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. No pressure, just an invitation. And now, let's begin. Imagine this. You're looking at a photograph of someone you love. You've seen this photo 1,000 times. You know the curve of their smile, the color of their eyes. You could describe it perfectly. And then one day, someone tells you the photograph was edited. The colors were enhanced. The contrast was pushed. And the person you thought you knew, the face you carried in your memory, it looked different all along. That's what happened with Neptune. In 1989, a spacecraft called Voyager 2 flew past Neptune. It was the first time, and still the only time, humanity had sent a machine to visit this distant world. Neptune is so far from Earth that light takes over 4 hours to travel between us. When Voyager's cameras turned toward the planet, they captured something extraordinary. A brilliant deep blue orb floating in the blackness, wrapped in white clouds, marked by a giant storm the size of Earth itself. Scientists called it the Great Dark Spot. Photographers called it magnificent. The world called it Neptune. But there was something the world didn't know. The engineers and scientists at NASA had deliberately enhanced those images. They increased the color saturation. They boosted the contrast. They did this for a reason: to make Neptune's atmospheric features visible, to help researchers study the storms, the clouds, the wind patterns that shaped this ice giant's face. In the original image releases, there were technical notes explaining this. Captions that said quietly, "Colors have been enhanced to reveal detail." But as decades passed, the captions faded. The explanations were forgotten. Only the images remained vivid, stunning, and not quite true. Neptune became famous for being intensely, impossibly blue. Uranus became known for its pale cyan hue. They looked nothing alike. Two siblings at the edge of the solar system, dressed in completely different colors. It seems strange, doesn't it, that we could be wrong about something so basic as color. But color in space is not as simple as it appears. When light from the sun reaches Neptune, traveling nearly 3 billion miles, it arrives weakened, diluted, almost exhausted. The light that bounces back to us carries information. Yes, but reading that information requires care, and for 35 years we misread it. In 2024, a team led by Professor Patrick Irwin at the University of Oxford decided to look again. They used data from the Hubble Space Telescope, specifically an instrument called the Space Telescope Imaging Spectrograph. Unlike regular cameras that capture images in separate color channels, this instrument records a continuous spectrum of light for every single pixel. Each point of data contains not just one color, but a rainbow of wavelengths, all measured precisely. They also used observations from the Very Large Telescope in Chile, an instrument with a beautiful name, the Multi-Unit Spectroscopic Explorer. Together, these tools allowed scientists to see Neptune's true color without ambiguity. No guessing, no combining separate images. Just pure unfiltered light, measured and understood. What they found was simple and startling. Neptune and Uranus are nearly the same color. Both are a pale greenish blue, like shallow tropical water under a cloudy sky. Neptune has only a slight hint of extra blue, not much, just a whisper of difference caused by a thinner haze layer in its atmosphere. But the deep dramatic azure we'd imagined, it never existed. Think about what this means. For more than 3 decades, every poster, every documentary, every mental image people carried of the outer solar system, it was built on an illusion, not a lie exactly. More like a well-intentioned mistake that became truth through repetition. Dr. Heidi Hammel, a planetary scientist who has spent her career studying these ice giants, said something striking when the corrected images were released. The misperception of Neptune's color has bedeviled us for decades. Bedeviled. As if the false blue had haunted the field, a ghost that wouldn't leave a beautiful error that lingered too long. Why does this matter? Why should we care about the exact shade of a planet 4.5 billion kilometers away? Perhaps because it reminds us that seeing is not the same as understanding. Our eyes, magnificent as they are, can be fooled. A photograph can tell a story that isn't quite true. Even science, careful and rigorous, can carry forward an image that needs correction. There's something almost human in this, isn't there? We enhance what we want to see. We saturate the colors of our memories, boost the contrast of our past. We remember things as more vivid than they were, and sometimes years later, we discover the truth was quieter, softer, less dramatic, but no less real. Neptune didn't change. It's been the same color for billions of years, spinning silently at the edge of everything we know. What changed was us, our instruments, our willingness to look again. Here's a question worth considering. How many other things do we think we know simply because we saw them once and never questioned again? The false blue of Neptune isn't just a story about astronomy. It's a story about human perception, about the way images become facts, about the gap between what we see and what is actually there. When Voyager 2 sent back those enhanced images in 1989, the world was captivated. Neptune became the blue planet of the outer solar system, a distant mirror to Earth's own oceanic hue. That narrative fit. It felt right. But feeling right and being right are different things. Scientists knew, of course. The researchers who worked on the Voyager mission understood the images had been processed, but knowledge doesn't always spread evenly. By the time Neptune's images reached textbooks, museums, popular science shows, the technical details had been stripped away. What remained was beauty mystery and a color that never quite existed. Professor Irwin, in describing his team's work, used a phrase that feels important. We have been able to reconstitute the most accurate representation yet of the color of both Neptune and Uranus. Reconstitute, to rebuild, to restore something to what it was before it was altered. In a way, that's what all science does. It looks at the world as we've constructed it, with our assumptions, our instruments, our inherited images, and asks, is this true, or is this just what we wanted to believe? Now, if you're imagining Neptune as dull or disappointing or less beautiful in its true colors, stop. Let that thought drift away. Because what we've learned about Neptune isn't a loss, it's a gift. The real Neptune is still astonishing. It's still a world of methane ice clouds and supersonic winds of storms that appear and vanish like thoughts of a thin haze layer that gives it just a touch more blue than its sibling Uranus. It's a world where the atmosphere is so cold that methane, the same gas that heats our homes, freezes into crystals and falls like snow. And beneath that, deeper than any spacecraft has seen, there may be oceans of liquid diamond. Pressures so intense that carbon atoms are crushed into gemstones, drifting slowly through layers of exotic ices, sinking toward a core we can only imagine. None of that changes just because the color in our photographs was wrong. If anything, knowing the truth makes Neptune more real, more knowable, more present in the universe as it actually exists. There's an older story here too, one that precedes Voyager, precedes photography, precedes even the telescope. It's the story of how Neptune was discovered in the first place, not by looking, but by calculating. Not by seeing, but by believing that mathematics could reveal what eyes could not. In the 1840s, astronomers noticed something odd. Uranus, the seventh planet, wasn't moving quite right. Its orbit had wobbles, irregularities that Newton's laws of gravity couldn't explain unless there was something else out there, something unseen tugging on Uranus with its invisible mass. Two mathematicians working separately decided to find that invisible thing. One was French Urbain Le Verrier, the other was English John Couch Adams. Neither knew the other was working on the same problem. Both arrived at the same conclusion: there must be an eighth planet. And both calculated where it should be. Le Verrier sent his calculations to an astronomer in Berlin named Johann Galle. On the night of September 23, 1846, Galle pointed his telescope to the position Le Verrier had predicted. Within an hour, less time than it takes to watch a movie, less time than it takes to fall asleep, he found Neptune. Not where Adams had predicted, but within 1 degree of Le Verrier's calculations. 1 degree. In the vastness of space, that's astonishing. François Arago, a prominent French astronomer, said of Le Verrier's achievement, "He discovered a star with the point of his pen." Just imagine that. No telescope, no spacecraft, just equations, patience, and trust in the laws of gravity. Neptune was the first planet found not by accident, not by scanning the sky, but by believing that mathematics described reality so precisely that numbers could see farther than eyes. And now, nearly 180 years later, we're still learning to see Neptune clearly, still correcting our vision, still discovering what was there all along, waiting for us to look with better tools, clearer understanding, more honest eyes. So here we are at the beginning of a longer story. Tonight we'll drift through the history of Neptune, how it was found, how it was seen, and what it really is beneath the beautiful lie we've been telling for decades. We'll talk about the fastest winds in the solar system, about diamond rain and backward moons, about time that moves differently at the edge of the sun's reach. But for now, let this thought settle: Neptune is not what we thought it was. And that's okay. Because the universe doesn't need our expectations to be magnificent. It just is. Softly blue-green, wrapped in methane clouds spinning in the cold and the dark. Neptune is real. More real now than it's ever been in our collective imagination. And sometimes the truth is quieter than the myth, but infinitely more worth knowing. The color was never the point, really. The point was always the looking, the returning, the willingness to say we were wrong and now we know better. That's not a failure, that's science breathing. And Neptune, patient and distant, has been waiting for us to see it clearly all along. Let's keep going. Let's learn how a planet can be discovered by someone who never saw it, by someone who believed in numbers more than light, and was proven right by the stars themselves. What if I told you that someone found a planet without ever looking through a telescope, not by accident, not by luck, but by sitting at a desk, writing equations, trusting that numbers could see what human eyes could not? And then, when someone finally pointed a telescope at the exact spot, those equations predicted there it was, a whole world hiding in plain darkness, waiting to be calculated into existence. That's how Neptune entered human awareness, not through light, but through gravity's whisper. It remains the only planet in our solar system discovered by pure mathematics, a triumph so profound that it changed how we think about knowledge itself. The story begins in 1781, 65 years before Neptune's discovery, when a musician and amateur astronomer named William Herschel spotted something unusual while surveying the night sky from his backyard in Bath, England. At first, he thought it was a comet, but as he observed it night after night, tracking its motion against the background stars, he realized it was moving too slowly, too steadily. It wasn't a comet at all. It was a planet. The seventh planet, Uranus. For the first time in recorded history, the solar system had grown. For thousands of years, humanity had known 6 wandering lights: Mercury, Venus, Mars, Jupiter, Saturn, and Earth itself. The discovery of Uranus doubled the known radius of the solar system overnight. It was thrilling. It was humbling. It suggested that perhaps there were more worlds out there silent and unseen waiting. But Uranus had a problem. As astronomers tracked its orbit year after year, they noticed something strange. Uranus wasn't moving quite right. According to Newton's law of universal gravitation, which had successfully predicted planetary motions for over a century, Uranus should have followed a smooth, predictable path around the Sun. But it didn't. It sped up when it should have slowed down. It drifted when it should have stayed true. The deviations were small, but they were real. Something was pulling on Uranus, something unseen. By the early 1840s, astronomers had a hypothesis. There must be another planet beyond Uranus exerting gravitational influence causing these wobbles. But finding it would be nearly impossible. The outer solar system is vast and dark. A planet that far from the Sun would be faint, too faint to see with the naked eye, difficult even with telescopes. Searching for it would be like trying to find a particular grain of sand on a beach at midnight, unless you knew exactly where to look. Enter two mathematicians working independently, separated by the English Channel, unaware of each other's efforts. In England, there was John Couch Adams, a young man fresh out of Cambridge University, brilliant and determined. In 1843, at just 24 years old, he decided to tackle the Uranus problem. For 2 years, he worked through extraordinarily complex calculations, accounting for the gravitational effects of the Sun, Jupiter, Saturn, and this hypothetical eighth planet. He had to predict not just where the planet was now, but where it had been for decades, how its gravity would have tugged on Uranus over time, creating the exact pattern of deviations astronomers had observed. By October 1845, Adams had his answer. He delivered his calculations to George Airy, the British Astronomer Royal, predicting the location of the unknown planet. But Airy was skeptical. He asked Adams follow-up questions. Adams didn't respond quickly. And in the delays and hesitations of academic correspondence, an opportunity slipped away. Meanwhile, in Paris, Urbain Le Verrier, a professor at the École Polytechnique, was working on the same problem. He had started later than Adams, but he worked with fierce intensity. By June 1846, Le Verrier presented his findings to the French Academy of Sciences. An eighth planet should exist at a specific location in the sky. He gave the coordinates. He gave the predicted mass. He even estimated the planet's orbital period. And then he did something Adams had not. He sent his calculations directly to an astronomer who could observe immediately. On August 34th, 1846, Le Verrier wrote to Johann Gottfried Galle at the Berlin Observatory. The letter arrived on September 23rd. That very night, that same night, Galle and his assistant, Heinrich d'Arrest, pointed their telescope to the spot Le Verrier had indicated. Within 1 hour of searching, they found it. A small bluish disk that wasn't on any star chart. It moved against the background stars just as a planet should. Neptune was there within 1 degree of Le Verrier's prediction. 1 degree. In a sky of 360 degrees in a solar system of unimaginable distances, Le Verrier's mathematics had pinpointed a world he'd never seen. François Arago, head of the Paris Observatory, famously declared, "He discovered a star with the point of his pen." And it was true. Le Verrier had looked at numbers, perturbations in an orbit, tiny irregularities in Uranus's motion. And from those numbers alone, he pulled an entire planet into human awareness. Now imagine being Galle that night. Imagine receiving a letter from Paris saying, "Point your telescope to this exact spot and you will find a new world." Imagine the skepticism you might feel. The universe is vast, predictions fail, hypotheses collapse, and yet you aim the telescope, you look, and there it is. Galle wrote back to Le Verrier with astonishment, "The planet whose place you have computed really exists." The emphasis on really feels important, as if Galle himself could barely believe that mathematics had this kind of power, that equations could reach across millions of miles and grasp something true. This was not just a discovery of a planet. It was a validation of an entire way of understanding reality. Newton's laws of gravity, which had been questioned and debated, were now confirmed at the very edge of the known solar system. Theory had predicted observation. Mathematics had led the way. It's worth pausing here to consider what this meant for humanity's relationship with the universe. For most of history, we discovered things by stumbling across them, by scanning the skies, by accident or persistence. But Neptune was different. Neptune was found by believing that the universe follows rules, and that those rules can be written down, understood, and used to see what hasn't yet been seen. The discovery sparked an immediate international controversy. When news of Neptune reached England, George Airy, the same astronomer who had dismissed Adams's calculations, suddenly announced that Adams had predicted Neptune's location even before Leverrier. Airy published Adams's work and tried to claim partial credit for England. The French were furious. Leverrier had done the work, published it, and acted on it. Adams had hesitated, been ignored, and only became relevant after the discovery was made. For months, the dispute raged. Who deserved credit? Was it the person who calculated first, or the person whose calculations actually led to the discovery? Eventually, history settled on a compromise. Both Adams and Leverrier are credited as co-discoverers of Neptune, along with Galilei, who was the first to knowingly observe it through a telescope. The Royal Society awarded Leverrier the prestigious Copley Medal in 1846 and gave Adams the same honor in 1848. When Adams later became president of the Royal Astronomical Society, it fell to him to present a medal to Leverrier, a moment of grace and reconciliation between rivals. But here's something interesting: both men were extraordinarily lucky. Leverrier and Adams assumed Neptune's orbit was roughly circular and used that assumption in their calculations. By pure chance, they happened to make their predictions during a period around the 1840s when Neptune was near the point in its orbit where a circular assumption worked reasonably well. If they had made the same calculations for Neptune's position 80 years earlier or later, their predictions would have been wildly inaccurate. Neptune's actual orbit is slightly elliptical, and that small difference would have thrown off their math significantly. They didn't know this. They couldn't have known. But luck and timing gave them the right answer anyway. Sometimes, even in science, fortune favors the bold. Neptune takes 165 years to orbit the Sun once. Leverrier and Adams caught it in just the right spot, at just the right moment in its long, slow journey. It's a reminder that discovery is often a mix of brilliance and chance preparation and timing. The universe doesn't always reward the perfect method. Sometimes it rewards the brave attempt made at exactly the right moment. There's one more layer to this story, one more twist worth considering. Neptune wasn't actually seen for the first time in 1846. It had been observed before recorded as a star in older astronomical surveys, but no one realized what it was. Galileo himself, the father of telescopic astronomy, observed Neptune in December 1612 and again in January 1613 while he was tracking Jupiter's moons. He even noted that one of the stars near Jupiter had moved slightly between observations. But he didn't follow up. He didn't recognize it as a planet. To him, it was just another faint point of light, one of thousands unremarkable. If Galileo had watched that star for a few more weeks, if he had noticed its steady drift against the background sky, he might have discovered Neptune 234 years earlier. But he didn't. He moved on to other things. And Neptune remained unknown, not because it was invisible, but because no one was looking in the right way. That's the nature of discovery, isn't it? Sometimes the thing you're searching for has been there all along, visible but unnoticed, waiting for the right question, the right tools, the right moment of attention. Leverrier's success with Neptune changed him. He became famous, celebrated across Europe, awarded honors and titles. A chair of astronomy was created for him at the University of Paris. In 1854, he became director of the Paris Observatory. But by most accounts, the fame did not improve his character. Colleagues described him as tyrannical, arrogant, impossible to work with. In 1870, after years of conflict with the observatory staff, he was forced to resign. When he was eventually reinstated, the tensions continued until his death in 1877. There's a biography of Leverrier with a striking title, Magnificent and Detestable Astronomer, both words fully earned. He discovered a planet with nothing but mathematics and determination. He also made the lives of those around him miserable. Genius and kindness, it turns out, are not always companions. But whatever his flaws, Leverrier proved something profound, that reality is knowable, that the universe speaks in the language of mathematics, and that sometimes, if you listen carefully enough to the numbers, they will show you worlds you've never seen. After Neptune, Leverrier tried to repeat his success. He turned his attention to Mercury, the innermost planet, which also had an orbital irregularity. Mercury's perihelion, the point in its orbit closest to the Sun, was advancing slightly faster than Newton's laws predicted. Leverrier calculated that there must be another planet even closer to the Sun, a small world he named Vulcan. Searches began. Some astronomers claimed to have seen it. Leverrier predicted when it would transit across the Sun's face. But Vulcan never appeared. The observations were mistakes, illusions, wishful thinking. There was no planet inside Mercury's orbit. Leverrier's method had failed, or rather, Newton's laws had failed. It would take another 50 years and a young physicist named Albert Einstein to explain Mercury's strange orbit not with a hidden planet, but with a completely new understanding of gravity itself. General relativity showed that space and time curve around massive objects, and that curvature explained Mercury's motion perfectly without needing Vulcan at all. Leverrier's failure teaches us something important. Even brilliant methods have limits. The universe doesn't always fit the tools we bring to it. Sometimes the answer requires not just better calculations, but entirely new frameworks of thought. But Neptune was real. Neptune was exactly where the mathematics said it should be. And in 1846, that was enough to change everything. It proved that the solar system could still surprise us. It proved that observation and theory could work together, each guiding the other toward truth. Think about what this means for how we know things. We trust our eyes, we trust photographs, we trust what we can see and touch. But Neptune taught us that sometimes the deepest truths are invisible, hidden not because they're far away, but because we're not looking in the right way. Mathematics saw Neptune before telescopes did. Equations pointed the way. And now, nearly 180 years later, we're still learning to see Neptune clearly. Still correcting the images Voyager sent us. Still discovering that what we thought we knew was only part of the story. The planet hasn't changed. Our vision has. Our tools have. Our willingness to look again, to question, to measure more carefully. So here's the real lesson of Neptune's discovery. The universe is patient. It waits for us to develop the tools, the methods, the courage to see what's really there. It doesn't care if we get the color wrong for 35 years. It doesn't care if we argue about who discovered it first. It just exists spinning in the dark, following the same gravitational laws that allowed two mathematicians in the 1840s to find it with nothing but pen and paper. And if mathematics could find a whole planet in 1846, what else might we discover if we trust the numbers, follow the data, and look where the equations point? The answer, as we'll see, is more than we ever imagined. Because Neptune itself, the actual planet, not just the discovery, holds mysteries far stranger than anyone in 1846 could have dreamed. Mysteries that took another 143 years and a spacecraft traveling billions of miles to finally reveal. But those mysteries didn't begin with spacecraft. They began with something simpler, with faith in the idea that reality makes sense, that patterns have meaning, that gravity's pull across empty space can be written down and understood. Leverrier believed that. Atoms believed that. And they were right. Sometimes before you can see something, you have to believe it's there. And sometimes, if you calculate carefully enough, the universe will prove you right. Imagine spending 12 years building a machine, launching it into space, and sending it on a journey so long that by the time it reaches its destination, the engineers who built it are approaching retirement. Imagine that machine traveling farther than any human-made object has ever gone past Jupiter, past Saturn, past Uranus, until finally on August 25th, 1989, it arrives at Neptune, 4.5 billion kilometers from home, alone in the dark. And then imagine it sends back photographs, so stunning, so vivid, so impossibly blue, that they become the defining image of an entire world for the next 35 years. That machine was Voyager 2, and those photographs, beautiful as they were not quite true. This is the story of a well-intentioned deception of how science itself created the illusion we've been trying to correct ever since. In 1977, NASA launched two identical spacecraft, Voyager 1 and Voyager 2. Their mission was audacious to visit the outer planets during a rare alignment that occurs only once every 176 years. Voyager 1 would fly past Jupiter and Saturn. Voyager 2 would go further, Jupiter, Saturn, Uranus. And if everything went perfectly, Neptune, everything did go perfectly, more or less. By the time Voyager 2 reached Neptune in August 1989, it had been traveling for 12 years. It was so far from Earth that radio signals moving at the speed of light took 4 hours and 6 minutes to reach us. When Mission Control sent a command to the spacecraft, they had to wait over 8 hours for confirmation that it had been received and executed. Every decision had to be made with that delay in mind. There was no room for real-time adjustments, no possibility of quick fixes. Voyager 2 was essentially on its own, executing pre-programmed instructions in the coldest, darkest region of the solar system humanity had ever reached. The spacecraft carried cameras, imaging systems built in the 1970s, designed to capture light across different wavelengths. But here's the crucial detail. Voyager's cameras didn't take color photographs the way a modern camera does. Instead, they took separate black and white images through different colored filters. One image through a blue filter, one through a green filter, one through an orange filter. Later, scientists would combine these separate images to create a composite color picture. And that's where the story gets complicated. When the first images of Neptune arrived back on Earth, scientists at NASA's Jet Propulsion Laboratory faced a choice. Neptune's atmosphere is dynamic, filled with high-altitude clouds, storm systems, bands of wind moving at different speeds. These features are scientifically valuable. They tell us about atmospheric circulation, about temperature gradients, about how energy moves through a gas giant's atmosphere. But in the raw, unprocessed images, many of these features were subtle, difficult to see. So the imaging team made a decision. They would enhance the images. They increased the color saturation to make Neptune's blue hue more prominent. They boosted the contrast to make the white methane clouds stand out sharply against the planet's darker regions. They adjusted brightness levels to reveal details in the Great Dark Spot, a massive storm system roughly the size of Earth. These weren't arbitrary changes. They were deliberate, scientifically motivated adjustments meant to help researchers study Neptune's weather patterns. And crucially, NASA included captions with the released images explaining that the colors had been enhanced to reveal atmospheric detail. The information was there, publicly available, technically accurate, but captions fade. Explanations get lost. Over time, the images travel further and further from their original context into textbooks, documentaries, museums, screensavers, posters, and classrooms. The technical details were stripped away. What remained was the image itself, Neptune impossibly dramatically blue, deeper blue than any ocean on Earth, blue like a sapphire held up to starlight. It was gorgeous. It was iconic. It was wrong. Here's what happened, technically speaking. In the composite images released to the public, the blue channel was weighted more heavily than it should have been. Think of it like adjusting the color balance on a photograph. If you push the blue slider too far, everything takes on a cold azure tint. That's essentially what was done to Neptune's images, but for scientific rather than aesthetic reasons. The scientists wanted to see the clouds. The clouds showed up better with enhanced blue. Uranus, by contrast, was processed more conservatively. Its images were closer to what astronomers call true color, what the planet would look like if you could see it with your own eyes from a spacecraft window. As a result, Uranus appeared as a pale, almost featureless cyan disk, while Neptune looked like a vibrant, storm-swept world of deep azure. The difference was striking. Two ice giants, similar in size and composition, seemingly dressed in completely different colors. For decades, this became the accepted reality. Textbooks would say, Neptune is blue, Uranus is cyan. Children learned this, scientists taught this. Everyone believed it because the photographs coming from NASA, from Voyager, from the edge of the solar system, felt unquestionably real. But photographs can lie even when they're technically accurate. Or rather, they can tell a truth that's been adjusted, filtered, processed, until it's no longer quite the truth it started as. Let me ask you something. Have you ever edited a photo on your phone, increased the saturation to make a sunset look more vivid, boosted the contrast to make details pop? Of course you have. We all have. And when we do that, we're not lying exactly. We're emphasizing, revealing, making visible what felt true to us in the moment, but didn't quite come through in the raw image. That's what NASA did with Neptune. They enhanced what was there, made it more visible, more dramatic, more useful for scientific study. The problem wasn't the enhancement itself. The problem was that the explanation got left behind. The image traveled into culture without its context, became truth by repetition, became so familiar that questioning it seemed almost heretical. Think about how often this happens. A simplification becomes the story. A vivid image replaces complex reality. And then years later, someone has to do the uncomfortable work of saying, actually, we got this wrong. Not wrong in the sense of lying, but wrong in the sense of incomplete, of too simple, of accidentally misleading. Neptune isn't lying about its color. We lied to ourselves by stopping at the beautiful image and never asking what had been done to create it. The irony is that planetary scientists knew all along. Researchers who worked on the Voyager mission understood that the public images were processed for visibility. When they published papers, they used different images carefully calibrated, color corrected, closer to reality. But that knowledge stayed within the scientific community. It didn't make it into the popular imagination. Dr. Patrick Irwin, who led the 2024 study that finally corrected Neptune's color, said something important. Although the familiar Voyager 2 images of Uranus were published in a form closer to true color, those of Neptune were in fact stretched and enhanced, and therefore made artificially too blue. Even though the artificially saturated color was known at the time amongst planetary scientists, and the images were released with captions explaining it, that distinction had become lost over time. Lost over time. That phrase is key. Truth doesn't just disappear because someone actively hides it. Sometimes truth fades simply because it's less interesting than the vivid image, less memorable than the striking story. The corrected color of Neptune, a pale greenish blue similar to Uranus, is accurate, but it's not as visually dramatic. It doesn't grab you the way the deep blue does. And in a world full of competing images and stories, the dramatic one wins even if it's not quite right. Here's the deeper question. Why does this matter? Neptune is still Neptune regardless of what color we think it is. The storms are still real. The winds are still the fastest in the solar system. The science isn't invalidated just because the color was wrong. So, why spend time correcting it? Because color is meaning. When we look at Neptune and see deep blue, we unconsciously associate it with depth, with mystery, with Earth-like qualities, our own planet's oceans. We build a narrative around that color. We imagine Neptune as fundamentally different from Uranus, when in reality they're siblings, nearly twins, separated by only subtle differences in atmospheric haze. Getting the color right isn't about pedantry. It's about seeing clearly. It's about not letting our inherited images, no matter how beautiful, prevent us from understanding what's actually there. Every false belief we carry, even a small one, is a barrier between us and reality. And science is the process of slowly, carefully removing those barriers. When we correct Neptune's color, we're not diminishing its wonder, we're honoring it. We're saying, you don't need to be artificially enhanced to be magnificent. Your real appearance is enough. The 2024 study that corrected Neptune's color used two sophisticated instruments, the Hubble Space Telescope's Space Telescope Imaging Spectrograph and the Very Large Telescope's Multi-Unit Spectroscopic Explorer. Unlike Voyager's cameras, which captured separate wavelengths and required manual color combination, these instruments record a continuous spectrum of light at every pixel. There's no ambiguity, no guessing about how to combine the channels. The color information is direct, unfiltered, precise. When researchers applied this data to reprocess the original Voyager images, the result was clear. Neptune and Uranus are both a similar shade of greenish blue. Neptune has slightly more blue, not dramatically, just a hint, because its atmospheric haze is thinner. Methane in the atmosphere absorbs red light, leaving blue and green to reflect back. With less haze, a bit more blue gets through. But it's a subtle difference, not the dramatic gulf we'd been seeing for decades. The researchers also figured out why Uranus looks slightly different at different times. During Uranus's solstices, summer and winter, when one pole points toward the sun, the planet appears slightly greener. During equinoxes, spring and fall, it looks slightly bluer. This happens because of a hood of methane ice particles that thickens over the poles during summer and winter. More ice means more scattering of blue light, which makes the polar regions look greener in comparison. These are the kinds of details you can only see when you measure carefully, when you look with instruments designed for precision rather than drama. And these details matter because they tell us about real physical processes, about how atmospheres respond to sunlight, about seasonal changes on a planet where each season lasts over 20 years. There's a pattern here worth noticing. First, we discover a planet through mathematics Leverrier's equations, pointing to Neptune's location. Then we photograph it with spacecraft Voyager's cameras, capturing its storms and clouds. And finally, we correct our vision with spectroscopy, measuring the light itself, not just capturing images. Each step gets us closer to the truth. Each step requires letting go of the previous certainty. That's hard. It's uncomfortable to be told that something you learned decades ago, something that felt rock solid and true, was actually a well-intentioned mistake. It's easier to keep believing the beautiful lie than to accept the quieter truth. But growth, intellectual, emotional, spiritual, always involves this kind of letting go. Neptune teaches us that even our most trusted sources can be wrong in subtle ways. Even NASA, even Voyager, even photographs from the edge of the solar system. Not because anyone was careless or dishonest, but because translation is always imperfect. Light becomes electrons, electrons become data, data becomes images, images become culture. And at each step, something can shift, something can be emphasized or downplayed, until what arrives at the end is true in some ways and false in others. The solution isn't to stop trusting, it's to keep questioning, keep measuring, keep looking with better tools. It's to hold our beliefs lightly enough that we can let them go when better information arrives. So here we are, more than 3 decades after Voyager 2's flyby, finally seeing Neptune clearly. The planet hasn't changed. It's been spinning there, pale greenish blue, wrapped in methane clouds, oblivious to how we've been portraying it. Our misconception didn't hurt Neptune, but it did hurt us in a small way. It put a false image between us. And reality made us think we understood when we were really just seeing through a filter. And now the filter is gone. Now we know. Neptune is not the deep blue giant we imagined. It's something quieter, subtler, more honest. It's a world that doesn't need dramatic enhancement to be worth studying, worth visiting, worth wondering about. The real Neptune is enough. It always was. But to see that we had to be willing to look again, to question our most familiar images, to trust that the truth, even when it's less vivid, is always worth finding. Because only when we see clearly can we begin to understand what we're really looking at. Only when we correct our vision can we start to ask the deeper questions. What is this world made of? How does its atmosphere work? What storms rage in its clouds, and what mysteries hide beneath? Those questions don't need false color to be compelling. They just need us to pay attention, to measure carefully, to be willing to be wrong so we can learn to be right. And that brings us to the next question, the one that matters most if we're going to truly see Neptune. Not just its color, but its light. Not just what it looks like, but how we know what it looks like. How do you measure the color of something 4.5 billion kilometers away? How do you see truly when seeing itself is so complicated, so filtered through instruments and data and human interpretation? The answer lies in understanding light itself, what it is, how it moves, and what it can tell us about worlds we'll never touch. Close your eyes for a moment. Now imagine trying to describe the color of something you've never seen, something so far away that the light reaching you left its surface before you were born. How would you even begin? That's the challenge astronomers face with Neptune. It's 4.5 billion kilometers from Earth, so distant that sunlight arriving there is 900 times weaker than the light warming your face right now. And yet, from that faint reflected glow, scientists can tell you not just what color Neptune is, but what it's made of, how cold it is, even what storms are brewing in its clouds. The secret isn't in looking harder. It's in learning to listen to what light is saying. Let's start with something fundamental. Color doesn't exist in the universe the way we think it does. Color is not a property of objects. It's a conversation between light and eyes, between wavelengths and perception. When you look at a red apple, you're not seeing redness as some inherent quality of the apple. You're seeing the wavelengths of light that the apple's surface didn't absorb. The apple took in all the blues and greens and yellows and reflected back only the reds. Your eyes caught those specific wavelengths, and your brain translated them into the experience you call red. Everything you see works this way. Color is subtraction. Color is what's left over after matter has taken what it needs and thrown the rest back at you. Now, imagine trying to see the color of something 30 times farther from the sun than Earth is. The light that reaches Neptune is already weak, filtered through billions of miles of empty space. The light that bounces back toward us is weaker still. By the time it reaches our telescopes, it's a whisper, a faint echo of the sunlight that began the journey. And from that whisper, we're supposed to determine truth. Neptune's color comes from methane. It's a simple molecule, one carbon atom bonded to 4 hydrogen atoms, floating in an atmosphere that's mostly hydrogen and helium. But methane has a particular property: it absorbs light in the red part of the spectrum. When white sunlight hits Neptune's atmosphere, the methane molecules grab the red wavelengths and hold them, converting that light energy into molecular vibrations, into heat. What's left to reflect back into space is mostly blue and green light. That's why Neptune appears blue-green. Not because it's made of blue-green material, but because it's made of material that eats red light. Uranus has methane too, roughly the same amount. So, why did we think for so long that the two planets look so different? The answer comes down to haze. Both planets have a layer of haze in their upper atmospheres. Tiny particles, photochemical smog, created when ultraviolet light from the sun breaks apart methane molecules and creates complex hydrocarbons. But Neptune's haze layer is thinner than Uranus's. With less haze scattering the light slightly more, blue wavelengths make it through on Neptune. It's a subtle difference, but it's there. A hint of extra blue in an otherwise similar palette. For decades, we missed this subtlety because we weren't measuring carefully enough. We were combining separate images, making choices about color balance, trusting that our processed composites were close enough to truth. But close enough isn't the same as correct. The breakthrough came from spectroscopy, the science of splitting light into its component wavelengths and measuring each one individually. Think of it like this: if a photograph is like hearing a full orchestra play, spectroscopy is like isolating each instrument and listening to it separately. You can hear exactly what the violins are doing, what the cellos contribute, which notes the flutes are emphasizing. You're not getting a general impression, you're getting precise information about every part of the whole. The Hubble Space Telescope's Space Telescope Imaging Spectrograph works on this principle. Instead of taking pictures through colored filters and combining them later, it captures a continuous spectrum of light at every single pixel. Imagine if every point in an image contained not just one color, but an entire rainbow, a complete record of which wavelengths are present and how strong each one is. That's what STIS does. It turns each pixel into a library of information. The Very Large Telescope in Chile has a similar instrument called MUSE Multi-Unit Spectroscopic Explorer. Despite its name, the Very Large Telescope is actually 4 separate telescopes working together with mirrors so precisely aligned that they can function as a single enormous eye staring at the cosmos. MUSE takes that combined light and spreads it into spectra, creating what astronomers call a data cube, a 3-dimensional structure where 2 dimensions are the image itself, and the 3rd dimension is wavelength. You can slide through this cube and see what the object looks like at different colors, what it looks like in pure red light, in pure blue, in infrared, in ultraviolet. With tools like these, there's no ambiguity about color. You're not guessing or estimating or balancing channels. You're measuring reality directly. Professor Patrick Irwin's team used data from both these instruments to reprocess the original Voyager 2 images of Neptune and Uranus. They took the raw, unenhanced data from Voyager's cameras, the separate black and white images captured through different filters, and combined them using the precise spectroscopic measurements from Hubble and the VLT as a calibration guide. It's like having a master key that shows you exactly how the puzzle pieces should fit together. What emerged was clarity. Neptune and Uranus, when properly color balanced, look remarkably similar. Both are pale greenish blue, with Neptune showing just a touch more blue due to its thinner haze. The dramatic difference we'd been seeing for 35 years wasn't real. It was an artifact of processing choices made for scientific purposes, but never corrected for public communication. Research shows that human perception is easily influenced by context and expectation. Once we've seen an image a certain way, especially if that image comes from an authoritative source like NASA, it becomes very difficult to see it differently. The enhanced blue of Neptune became the truth, not because it was measured carefully, but because it was repeated consistently. We saw what we expected to see, and we stopped questioning. That's one of the most common mistakes in science communication, assuming that a vivid image equals an accurate image. Drama and truth are not the same thing. Sometimes the most accurate representation is also the most subtle, the most careful, the least immediately striking. And in a world that rewards spectacle, subtlety often loses. Here's where it gets fascinating. Light carries more information than just color. The spectrum of light reflected from Neptune tells us about temperature, about chemical composition, about atmospheric pressure at different altitudes. When methane absorbs red light, it doesn't just disappear. It leaves gaps in the spectrum, dark lines where certain wavelengths are missing. Scientists can measure those gaps with extraordinary precision and use them to calculate how much methane is present and at what layers of the atmosphere. They can also detect other molecules. Traces of ethane and acetylene show up as tiny absorption features in the infrared part of the spectrum. Hydrogen and helium, which make up the bulk of Neptune's atmosphere, reveal themselves through different spectral signatures. Even the temperature can be inferred from the way molecules vibrate and rotate from the broadening of spectral lines due to thermal motion. It's like reading a language written in light, Inder. Each wavelength is a word, each absorption line is a punctuation mark, and together they tell a story about a world we've never touched. Think about that for a moment. We're 4.5 billion kilometers away from Neptune, separated by a gulf so vast that it takes light over 4 hours to cross it. We've sent exactly one spacecraft past that world, and it flew by in a matter of hours, never to return. Everything else we know comes from light, from photons that left Neptune's cloud tops, traveled through empty space for hours, and arrived at our telescopes, carrying information encoded in their wavelengths. And from those photons alone, we can reconstruct an entire planet. We can map its storms, measure its winds, determine its composition, calculate its temperature, and, yes, finally see its true color. That's not just science. That's almost like magic, except it's real, and it's repeatable, and it works. There's a deeper lesson here about how we know things. We tend to trust our eyes. Vision feels direct, immediate, unmediated. But seeing is always an interpretation. Light enters your eye, strikes your retina, triggers chemical reactions in photoreceptor cells, generates electrical signals that travel through your optic nerve and finally get processed by your visual cortex into the experience of sight. Every step involves translation, filtering, interpretation. Your brain is constantly making choices about what to emphasize, what to ignore, what to construct into the coherent image you experience as seeing. Telescopes and spectrographs do something similar, but more carefully. They translate light into data, into images into understanding. And when we do it right, when we measure precisely, calibrate carefully, and resist the temptation to enhance for drama, we can see truths that would otherwise remain hidden. Neptune's true color was always there encoded in the light. We just needed better tools and more careful methods to read it correctly. The planet didn't change. Our ability to listen to what it was telling us changed. Let me ask you something. What else might we be seeing wrong? What other inherited images, accepted facts, comfortable certainties might be subtly incorrect, waiting for someone with better tools to look again? The history of astronomy is full of these corrections. We thought Mars had canals until better telescopes showed they were optical illusions. We thought the universe was static until Edwin Hubble measured the redshift of distant galaxies and proved it was expanding. We thought Pluto was planet-sized until careful observations revealed it was much smaller. Each correction felt like a loss. At first, a cherished belief dismantled, a familiar picture erased. But each correction also brought us closer to reality, to the universe as it actually is, rather than as we'd imagined it. Neptune's color is just the latest in this long tradition of looking, again measuring more carefully, being willing to say, we got that wrong, and now we know better. And knowing better doesn't diminish Neptune. If anything, it makes the planet more real, more knowable, more present in our understanding. The false blue was beautiful, yes, but it was also a barrier, a pretty lie that stood between us and truth. Now, that barrier is gone. Now we can see Neptune clearly, and that clear sight is worth more than any enhanced image, no matter how striking. Spectroscopy also revealed something unexpected about Uranus. Its color changes slightly with the seasons. During solstices, when one of Uranus's poles points toward the sun, the planet appears slightly greener. During equinoxes, when the sun shines more directly on the equator, it looks slightly bluer. This happens because of methane ice clouds that form over the poles during summer and winter. Uranus has a peculiar tilt. Its axis is tilted 98 degrees, meaning it essentially rolls around the sun on its side. During summer at the North Pole, that pole points almost directly at the sun and stays illuminated for 42 Earth years straight. During that long summer, methane in the upper atmosphere freezes and forms a hood of ice crystals over the pole. These crystals scatter light differently than gas molecules do, reflecting more green and red light compared to blue. The result is that the polar regions look slightly greener. When astronomers from the Lowell Observatory in Arizona looked at observations of Uranus taken from 1950 to 2016, they could see this subtle color shift happening over the decades as Uranus moved through its 84-year orbit. It's a slow change, barely noticeable year to year, but undeniable over time. And it's only visible because spectroscopy allows us to measure color precisely enough to detect these small variations. Neptune, despite being nearly a twin to Uranus in size and composition, doesn't show the same seasonal color changes. Scientists suggest this might be because Neptune has a stronger internal heat source, creating more atmospheric convection and preventing the formation of stable polar hoods. But the full answer is still being studied, still being measured, still revealing itself one spectrum at a time. Light, in the end, is the only messenger we have from most of the universe. We can't touch Neptune. We can't bring back samples. We can't send probes to every interesting place and see it directly. What we can do is learn to read light with extraordinary care, extracting every bit of information it carries, trusting that the universe is consistent, that the same physics applies everywhere that light tells the truth, if we know how to listen. And sometimes listening to light means discovering that what we thought we knew was incomplete, that the dramatic blue of Neptune was an enhancement, not reality, that the universe is often subtler, quieter, less immediately spectacular than our processed images suggest, but no less magnificent for being true. Neptune is pale greenish blue. That's the fact. That's what the light says when we measure it carefully. And that simple truth is worth more than any false drama, any enhanced color, any beautiful lie we might tell ourselves, because the real thing seems less exciting. The real thing is never less exciting, it's just more honest. And honesty in science, as in life, is the only foundation on which understanding can be built. So now we know what Neptune looks like. We know its color, its subtle differences from Uranus, its seasonal variations and atmospheric haze. We've learned to see it clearly, to trust our instruments more than our inherited images, to let go of the false blue and embrace the real thing. But color is only the beginning. Neptune is not just a colored disk in a telescope. It's a world, a vast, complex, dynamic world, with an interior we've never seen, made of materials under conditions we can barely imagine. And if we want to truly understand Neptune, we need to look deeper than its surface. We need to ask what lies beneath those pale blue-green clouds in the crushing darkness, where pressure turns ice into something strange and unfamiliar. We need to go inside. What if I told you that right now, deep inside Neptune, it's raining diamonds, not metaphorically, not poetically. Actually raining, crystallized carbon falling through layers of superheated liquid, sinking slowly toward a core we've never seen, in conditions so extreme that the rules of matter itself start to bend. Gemstones the size of raindrops drifting through darkness, pulled by gravity through an ocean that isn't water, in a world where ice is hot and pressure turns gas into something that shouldn't exist. Neptune is not what you think it is. And what lies beneath its clouds is stranger than almost anything else in our solar system. Let's start with a common mistake. When astronomers call Neptune an ice giant, most people imagine a frozen world, a solid sphere of ice floating in the cold darkness of the outer solar system. But that image is completely wrong. Neptune isn't frozen. In fact, most of it is blazingly hot, thousands of degrees compressed by pressures that would crush any spacecraft we could build into a speck of metallic dust. The ice in ice giant doesn't mean frozen water. It's an astronomical term, a category that describes certain materials based on what they're made of, not their temperature. In planetary science, ices means molecules like water, methane and ammonia, substances that are more complex than hydrogen and helium, but lighter than rock and metal. These ices can be solid, liquid, or gas, depending on temperature and pressure. Deep inside Neptune, there's something else entirely. A hot, dense fluid under such extreme conditions that it behaves in ways that don't match any familiar state of matter. Neptune isn't a gas giant like Jupiter or Saturn, where hydrogen and helium dominate all the way down. And it's not a rocky planet like Earth, with a solid surface you could stand on. It's something in between, a world where the atmosphere gradually becomes denser and hotter as you descend, transitioning smoothly from gas to liquid to exotic compressed phases until finally, thousands of miles down, you reach a core of rock and metal, roughly the size of Earth. There's no surface to land on, no boundary between air and ground. just pressure increasing relentlessly until the very concept of air stops making sense. Let's take a journey downward, layer by layer, into Neptune's interior. Picture yourself descending through the atmosphere in an imaginary probe, one that can somehow withstand the conditions we're about to encounter. You begin at the cloud tops, where the temperature is around 55 Kelvin, that's minus 360 degrees. Fahrenheit cold enough that your breath would freeze solid before it left your lungs. The atmosphere here is thin, hazy, composed mostly of hydrogen and helium with traces of methane. Pressure is about 1 bar, roughly the same as Earth's atmosphere at sea level. You could breathe here if the composition were different and the temperature didn't kill you instantly. As you descend, the atmosphere gets denser. Temperature rises slowly at first. Within a few hundred miles, you pass through layers of methane ice clouds, thin, wispy cirrus formations made of frozen methane crystals. These clouds cast shadows on lower cloud decks, shadows that Voyager 2 photographed from 35 million miles away, allowing scientists to calculate that these upper clouds float about 50 miles above the main cloud layer. Lower still, around 1.5 bars of pressure, you encounter the main methane cloud deck, the layer that gives Neptune its pale blue-green color. Below this, the atmosphere becomes opaque. No sunlight penetrates deeper. You're entering a realm of perpetual darkness, lit only by the faint heat radiating from Neptune's interior. At 3 bars of pressure, you might pass through clouds of hydrogen sulfide, the same compound that gives rotten eggs their smell. On Neptune, it forms ice particles suspended in the crushing atmosphere. Particles we've never directly observed, but predict must exist based on chemical models and comparisons with other planets. Deeper. 5 bars of pressure. You're miles below the cloud tops now, and the temperature is climbing up to 273 Kelvin 0 degrees Celsius, the freezing point of water on Earth. Here scientists suggest there may be clouds of ammonia, ice mixed with water ice, though Neptune is so cold overall that ammonia remains mostly frozen. But you're still in the atmosphere. The real Neptune, the bulk of the planet's mass, lies much deeper. Keep descending. 10 bars, 20, 50. The hydrogen and helium around you are getting thicker, denser, transitioning from gas toward liquid without any clear boundary. Temperature is rising steadily now, hundreds of degrees, then 1,000. The pressure is immense, squeezing the atmosphere into a state that's neither quite gas nor quite liquid. Chemists would call it as supercritical fluid, a phase of matter, where the distinction between liquid and gas breaks down completely. Around 100 bars of pressure, you transition out of what we'd call the atmosphere and into the mantle, a vast ocean of water, methane and ammonia under conditions Earth has never seen. But don't imagine it as a calm sea. This ocean is hot thousands of degrees Celsius, kept liquid not by temperature, but by pressure, so intense it prevents the molecules from evaporating. It's a scalding electrically conductive soup, possibly with currents and convection cells larger than continents. And this is where things get truly strange. This is where Neptune might be raining diamonds. The idea sounds like science fiction, but the physics is sound. In 2017, researchers at the SLAC National Accelerator Laboratory in California conducted an experiment. They took samples of polystyrene, a plastic that contains carbon and hydrogen in ratios similar to methane, and subjected them to conditions matching what exists about 6,000 miles below Neptune's surface. They used high-powered lasers to create pressures of millions of atmospheres and temperatures of thousands of degrees conditions that could only be maintained for a nanosecond before the equipment failed. In that nanosecond, something remarkable happened. The carbon and hydrogen in the plastic separated. The carbon atoms, under such extreme pressure and temperature, crystallized into diamonds, tiny nanometer-scale gems that formed almost instantly from the molecular chaos. The researchers watched it happen, captured it on instruments, proved that the process was real. Scientists suggest that on Neptune, this process happens continuously. Methane molecules abundant in Neptune's mantle break apart under pressure and heat. The carbon atoms drift together, bond, crystallize into diamond. These diamonds, being denser than the surrounding fluid, sink slowly downward through the mantle like rain, falling for years, perhaps decades, through thousands of miles of hot, compressed ocean. Eventually, they reach the core, a solid region of rock and metal, roughly 10 to 15 times Earth's mass. There, the diamonds might float on a sea of liquid carbon, or accumulate in vast deposits, or be crushed into even stranger forms of matter. We don't know. We've never been there. We can only calculate, model, hypothesize. But the diamonds are almost certainly real. Too many independent experiments, too many theoretical models, too much consistency across different approaches. Neptune's interior is a place where one of Earth's most precious substances falls from the sky like snow, unwitnessed, unvalued, eternal. Think about that for a moment. An entire planet's worth of diamonds raining through darkness in a place no human will likely ever visit. It's a strange kind of wealth, infinite and worthless at the same time. The diamonds exist, but they might as well not, because they're forever beyond reach, forever inaccessible, serving no purpose except to sink slowly through an alien ocean under pressure that would annihilate anything we could send there. It makes you wonder about value, doesn't it? We prize diamonds on Earth because they're rare, because they're difficult to create, because they symbolize permanence and commitment. But on Neptune, they're just precipitation weather, in a place where weather is measured in tons of crystallized carbon per cubic kilometer. Perhaps that's the lesson: rarity is contextual. Beauty is contextual. What matters in one place means nothing in another. The universe is full of wonders, but most of them exist in conditions where wonder itself is impossible, where there are no eyes to see, no minds to appreciate, only physics playing out its patterns in the dark. The mantle makes up the bulk of Neptune's mass, roughly 10 to 15 Earth masses of water, methane, ammonia, and their breakdown products. That's an ocean larger than all of Earth, compressed into a layer perhaps 5,000 miles thick, surrounding the core. This ocean is not uniform. There are likely convection currents, hot fluid rising from near the core, cooler fluid descending from above, driven by the heat flowing outward from Neptune's interior. And here's something fascinating: this ocean might be electrically conductive. When methane breaks down under pressure, it can release ions, charged particles that move freely through the fluid. These ions could carry electrical current. And if there are currents flowing and the ocean is moving through convection, then Neptune's interior might generate electrical fields, might create its own system of circulating charges that influences the planet's magnetic field. Neptune's magnetic field is strange, tilted 47 degrees from its rotation axis and offset from the planet's center. It's not a simple dipole like Earth's magnetic field. Scientists suggest this complex field structure might arise from electrical currents in the icy mantle rather than in the core. The moving, conducting ocean generates the field not through the dynamo process that powers Earth's magnetism, but through some other mechanism we're still working to understand. It's another reminder that Neptune doesn't follow Earth's rules. Different materials, different pressures, different physics. The same fundamental laws apply, but the outcomes are alien. At the very center lies the core, a solid sphere of silicate rock and nickel-iron metal, roughly the mass of Earth, possibly larger. The temperature here might reach 5,000 Kelvin, almost as hot as the sun's surface, but kept solid by pressures of millions of atmospheres. This core is a remnant of Neptune's formation, the rocky and metallic material that first coalesced in the early solar system, around which lighter materials later accumulated. We know surprisingly little about this core. Its exact size, composition, and state are all inferred from Neptune's mass, radius, and gravitational field. When Voyager 2 flew past Neptune, it measured how the planet's gravity affected the spacecraft's trajectory. From those tiny accelerations, changes in speed, measured in millimeters per second, scientists could calculate Neptune's mass distribution, infer how dense different layers must be built models of what lies inside. But models are not the same as knowledge. There's a lot of uncertainty. The core might be pure rock, or it might be mixed with ices. It might be uniform, or it might have layers: an inner core of iron, an outer core of rock. It might be partly molten or entirely solid. We simply don't know. What we do know is that Neptune, like Uranus, is not made the way Jupiter and Saturn are. The gas giants are mostly hydrogen and helium, the same composition as the Sun, essentially miniature stars that never quite got large enough to ignite fusion. But Neptune is richer in heavier elements. Its ices and rock make up a much larger fraction of its total mass. It's less a failed star, and more a water world gone wrong. A planet where the materials we associate with moons and comets became the dominant component, mixed with enough hydrogen to create a massive atmosphere, but not enough to overwhelm everything else. This raises a question astronomers have been puzzling over for decades. Why are Neptune and Uranus so different from Jupiter and Saturn? If they all formed from the same primordial cloud of gas and dust, why did the outer two ice giants end up with such different compositions? The most widely accepted theory is that Neptune and Uranus formed later, or formed farther out, or formed in a region where most of the available hydrogen and helium had already been captured by Jupiter and Saturn. By the time Neptune was assembling, there wasn't much light gas left. What remained were the heavier materials, ices and rock, so that's what Neptune accumulated. It grew slowly, taking millions of years to reach its current size, and by the time it was large enough to pull in significant hydrogen and helium, the sun's radiation had blown most of it away. Another possibility is that Neptune originally formed closer to the sun and migrated outward over millions of years, scattered by gravitational interactions with the other giant planets. Computer models of the early solar system suggest this kind of migration happened, that the planets didn't form where we see them today, but moved around exchanging positions, settling into their current orbits through a chaotic dance of gravity and momentum. If that's true, then Neptune might have originated as a closer neighbor to Jupiter and Saturn, and only later drifted to the cold outer edge where it sits now. Its composition would reflect where it formed, not where it ended up. A planetary refugee carrying the signature of its birthplace into permanent exile. We don't know for certain. We may never know. The early solar system left few records. All we have are the planets themselves, frozen in time, carrying clues about their origins encoded in their mass, their orbits, their moons. Here's something that surprised scientists when they studied Neptune more carefully. The planet radiates more heat than it receives from the sun. Neptune puts out 2.6 times more energy than solar heating can account for. That excess heat has to come from somewhere. One explanation is that Neptune is still warm from its formation 4.5 billion years ago. When the planet assembled from smaller pieces, all the infalling material released gravitational energy, potential energy converted to heat as matter fell inward and compressed. In a planet as massive as Neptune, that heat is enormous. And because Neptune is so large with so much mass insulating its interior, that primordial heat escapes very slowly. It's still leaking out, still warming the planet from within billions of years after the fires of formation cooled. Another possibility involves methane. Some scientists have suggested that Neptune's methane acts as an insulating layer, trapping heat in the interior more effectively than Uranus's atmosphere does. If that's true, then Neptune might have retained more of its formation heat simply because it's better insulated a planetary thermos, keeping its interior warmer longer. Or the heat might come from ongoing processes from chemical reactions in the mantle, from the slow crystallization of materials settling toward the core, from the very diamond rain we talked about. When carbon crystallizes out of the mantle, it releases energy. That energy becomes heat. If diamonds are constantly forming and falling, then Neptune has an internal heat source that's been active for billions of years and will continue for billions more. Whatever the source, the heat matters. It drives convection in the atmosphere, creates weather powers, the fastest winds in the solar system. Without that internal heat, Neptune would be quiet, still featureless, like Uranus. The extra energy makes Neptune dynamic, active, alive, in a way its sibling is not. It's the difference between a sleeping giant and one that's restless, always moving, never quite at peace. So here's Neptune, layer by layer, a thin atmosphere of hydrogen, helium, and methane, clouds of ice floating in the cold, a transition zone where gas becomes liquid, a mantle of hot compressed water, and methane, an ocean larger than Earth where diamonds fall like rain, a core of rock and metal, hot as the sun's surface, solid under crushing pressure, and threading through it all convection currents, electrical fields, flows of heat and matter, too vast to comprehend, operating on time scales measured in millions of years. This is what lies beneath the pale greenish-blue clouds we see from Earth. This is the reality of Neptune, not just a colored disk in a telescope, but a world of layers and phases and exotic materials, a laboratory of extreme physics, a place where the familiar rules of matter stretch and bend into forms we're only beginning to understand. And none of it would be visible without mathematics, without spectroscopy, without the patient accumulation of measurements and models. We can't go there. We probably never will. But we can calculate, we can infer, we can piece together the story from gravity measurements and heat radiation and laboratory experiments that recreate those impossible conditions for a fraction of a second. Science is the art of seeing what you can't see, of knowing what you'll never touch, of building truth from fragments and echoes, and the conviction that the universe follows rules we can discover. And Neptune, distant cold wrapped in mysteries, is one of the finest examples of that art. A world revealed not by visiting, but by thinking carefully about what light and gravity and physics are telling us. Now, we've seen inside, Neptune's seen the ocean and the diamonds and the impossible heat at its heart. But a world is more than its interior. A world is also its weather, its winds, its atmosphere and motion. And Neptune's atmosphere is among the most violent, most dynamic, most perplexing in the entire solar system. A place where storms the size of Earth appear and vanish like thoughts, where winds race at speeds that should be impossible, driven by an energy source we're still trying to fully understand. Imagine wind so fast it could circle the Earth in 4 hours. Not hurricane wind, not jet stream wind. Wind moving at 1,300 miles per hour, faster than the speed of sound, faster than a bullet, faster than anything on Earth, except explosions and spacecraft. Wind that never stops, never slows, racing endlessly around a planet where a day lasts only 16 hours, and the sun is a distant cold pinpoint of light. That's Neptune. And the strangest part isn't how fast the winds blow. It's that they exist at all on a world that should be too cold, too far from the sun, too starved of energy to have weather this violent. Something is driving these winds, something powerful, and we're still trying to understand what. When Voyager 2 flew past Neptune in August 1989, one of its primary missions was to study the planet's atmosphere to measure cloud movements, track storms, understand the weather on a world no spacecraft had ever visited. The images that came back were shocking. Neptune's atmosphere was alive with features bright white clouds streaking across the blue-green face, dark oval storms, reminiscent of Jupiter's great red spot, bands of wind circling the planet at different latitudes. But it was the wind speeds that truly astonished scientists. By tracking how fast the clouds moved across Neptune's face, researchers calculated that winds in the planet's equatorial region blow westward opposite to the planet's rotation at speeds up to 1,300 miles per hour. That's about 3 times faster than the fastest winds on Jupiter and 9 times faster than the most powerful hurricanes ever recorded on Earth. Think about what that means. On Earth, the most destructive hurricanes, Category 5 storms that flatten entire cities, have wind speeds around 150 to 180 miles per hour. On Neptune, that would barely register. The sustained constant everyday winds on Neptune blow 7 times faster than Earth's worst natural disasters. And here's the puzzle. Neptune receives only 0.1% of the solar energy that Earth does. At 30 times Earth's distance from the sun, sunlight arrives weak, diluted, almost powerless. There's simply not enough energy from the sun to drive weather this extreme. And yet Neptune has the most violent atmospheric dynamics in the solar system, more active than Jupiter, which receives 25 times more sunlight, more chaotic than Saturn, which is twice as close to the sun. How is this possible? The answer seems to lie in Neptune's internal heat. As we discussed earlier, Neptune radiates 2.6 times more energy than it absorbs from sunlight. That extra heat, whether from primordial warmth left over from the planet's formation, or from ongoing processes like the crystallization of diamonds in the mantle, rises from the interior and creates instability in the atmosphere. Warm gas rises, cool gas sinks, and the temperature difference between the heat source below and the cold cloud tops above drives massive convection currents. Scientists suggest that it's this internal heat, not solar heating, that powers Neptune's winds. The energy comes from within, pushing upward, creating pressure differences and temperature gradients that set the atmosphere in motion. And because Neptune rotates quickly once every 16 hours, the Coriolis effect twists these convection currents into the fierce, organized wind patterns we observe. But there's still something puzzling. Uranus-Neptune's near twin has almost no internal heat source. Uranus radiates only about as much energy as it receives from the sun, with no significant excess. And Uranus's atmosphere is calm, nearly featureless, almost boring compared to Neptune's. The two planets are similar in size, similar in composition, similar in distance from the sun. Yet their weather couldn't be more different. Why? What makes Neptune so restless and Uranus so quiet? We don't fully know. Some scientists think it has to do with the angle of rotation. Uranus spins on its side with a 98-degree tilt, while Neptune's tilt is only 28 degrees more Earth-like. Others point to differences in atmospheric chemistry or subtle variations in how heat escapes from each planet's interior. But the complete answer remains elusive, another mystery in the long list of things we don't yet understand about these distant worlds. Let's talk about Neptune's storms, the dark spots that appear and vanish like ghosts, leaving scientists scrambling to understand where they come from and where they go. When Voyager 2 observed Neptune in 1989, it captured images of a massive dark oval in the planet's southern hemisphere at about 22 degrees south latitude. Scientists called it the Great Dark Spot, an obvious nod to Jupiter's Great Red Spot. The similarity was striking. Both were anticyclonic storms. Both were enormous. Both occupied roughly the same proportion of their planet's surface. Neptune's Great Dark Spot was about the size of Earth, roughly 8,000 miles long and 4,000 miles wide. It rotated counterclockwise, completing one full turn every 18 days. Around the edges of the dark spot, Voyager photographed bright white clouds, methane ice crystals condensing at high altitudes, forming streaks and patches that change shape in a matter of hours. These companion clouds seemed to hover above the dark spot, almost like flags marking the location of something powerful and turbulent below. Scientists assumed reasonably that the Great Dark Spot was a permanent, or at least long-lasting feature, similar to Jupiter's storm, which has persisted for centuries. But when the Hubble Space Telescope turned its gaze to Neptune in 1994, the Great Dark Spot was gone, completely vanished. In just 5 years, a storm the size of Earth had dissipated, leaving no trace. Where did it go? The answer reveals something fundamental about Neptune's atmosphere. Unlike Jupiter, where wind bands act like rails keeping storms locked in place, Neptune's wind currents are much broader and less constrained. Storms can drift slowly across latitudes, moving from the mid-latitudes where they form toward the equator. And as they approach the equatorial wind jet, where winds blow strongest, the shear forces tear them apart. The dark spot is stretched, distorted, pulled into thin wisps, and eventually absorbed back into the surrounding atmosphere. Research shows that Neptune's dark spots typically last between 2 and 6 years. They're born in the mid-latitudes, drift toward the equator, and die. Some dissipate before reaching the equator, others make it farther, but none persist indefinitely. They're transient, ephemeral, temporary disruptions in an atmosphere that's constantly churning, constantly rearranging itself. Since Voyager's flyby, Hubble has observed several more dark spots. In 2018, astronomers spotted a new dark storm in Neptune's northern hemisphere, the first time a dark spot had been observed forming from the beginning. And here's where it gets interesting. Before the dark spot became visible, small, bright clouds appeared in the same region several years earlier. These bright companion clouds seemed to form before the dark spot, not after. They're a warning sign, a precursor indicating that something is building in the deeper atmosphere. This suggests that Neptune's dark spots don't form at the cloud tops where we see them. They originate much deeper, perhaps hundreds of miles down, where pressure and temperature are higher. As the storm grows and rises, it creates disturbances in the upper atmosphere that manifest as bright methane clouds. Only later does the dark spot itself become visible, punching through the haze layer and appearing as a dark oval against Neptune's blue-green face. Think of it like watching the surface of the ocean. Sometimes you see whitecaps and foam long before you see the swell underneath. The visible turbulence is a symptom of something deeper, something more powerful that hasn't yet revealed itself fully. Neptune's bright clouds are the whitecaps. The dark spots are the swells. Here's a question worth considering. What are these dark spots actually? What are we seeing when we look at them? They're not solid objects, not holes in the atmosphere. Scientists suggest they're anticyclonic storms, regions where gas circulates in the opposite direction to the planet's rotation, creating high-pressure systems. The darkness comes from the altitude. The storm pushes down on the atmosphere below, compressing it, clearing away the upper haze. We're seeing deeper into Neptune's atmosphere than we normally can, looking down through relatively clear air into darker lower cloud layers. The bright clouds around the edges form because air is rising at the boundaries of the storm. As it rises, it cools. Methane condenses into ice crystals, creating visible clouds. It's similar to how clouds form on Earth at the edges of low-pressure systems, where warm air is forced upward and moisture condenses. Different chemistry, same basic physics. But there's still so much we don't understand. We don't know exactly what triggers the formation of these storms. We don't know why they form at specific latitudes. We don't know why some last longer than others, or why they sometimes appear in clusters. Hubble's observations have given us snapshots, but snapshots aren't the same as understanding. They're moments in a story we're still learning to read. Let's compare Neptune to Jupiter for a moment, because the comparison reveals something important about how planetary atmospheres work. Jupiter's Great Red Spot has been continuously observed for at least 150 years, possibly longer. Historical records suggest that early telescopic observers may have seen it as far back as the 1600s, though we can't be certain those observations referred to the same feature. What we know for sure is that the Great Red Spot is persistent, anchored in place by Jupiter's tightly banded wind patterns, which act like grooves on a record, keeping the storm locked at a specific latitude. Neptune doesn't have those tight bands. Its wind patterns are broader, more diffuse. Storms have more freedom to move, which means they also have more opportunities to encounter conditions that destroy them. On Jupiter, a storm can sit in one place for centuries, stable and unchanging. On Neptune, stability is temporary. Everything drifts, everything changes. It's a difference in personality almost. Jupiter is steady, methodical, its weather following patterns that persist across centuries. Neptune is restless, impulsive, its atmosphere constantly rearranging itself. Both are beautiful. Both are scientifically valuable. But they teach us different lessons about how worlds behave when they're given different ingredients, different amounts of heat, different rotation speeds, different internal structures. There's no right way for a planet to have weather. There's just the way each planet does it, shaped by its history, its composition, its distance from the sun. And each way reveals something new about the physics governing atmospheres everywhere, including our own. The winds themselves follow patterns we're still mapping. Neptune has what astronomers call differential rotation. Different parts of the atmosphere rotate at different speeds. Near the equator, winds blow westward at enormous speeds, moving opposite the planet's rotation. At higher latitudes, winds blow eastward in the same direction as the rotation. The boundary between these wind zones is a region of intense shear, where adjacent layers of atmosphere are moving in opposite directions at hundreds of miles per hour. On Earth, wind shear like that would create violent turbulence. On Neptune, it probably does too, though we've never measured it directly. The storms we see, the dark spots, the bright clouds are likely manifestations of this turbulence regions, where the shearing forces become organized into coherent structures, eddies in the flow that grow large enough to be visible from billions of miles away. One of the most surprising discoveries from Hubble's long-term monitoring of Neptune is that the planet's cloud cover seems to vary with the sun's 11-year activity cycle. When the sun is more active, producing more ultraviolet radiation, Neptune develops more clouds in its upper atmosphere. When solar activity decreases, the clouds thin out. The correlation is striking, but the mechanism is unclear. How does Neptune's atmosphere so far from the sun respond to variations in solar output that are relatively small compared to the vast distance separating them? Scientists suggest it might involve photochemistry, ultraviolet light from the sun, breaking apart methane molecules in Neptune's stratosphere, creating hazes and clouds through chemical reactions. When solar UV increases, more methane gets broken down, more haze forms, more clouds appear. But the details are still being worked out, still being modeled, still awaiting more observations to confirm or refine the hypothesis. Here's something that humbles me. Every fact I've just shared about Neptune's winds, every measurement of storm size and wind speed and cloud altitude, it all comes from one spacecraft flyby, lasting a few hours and decades of patient telescopic observation from 4 billion kilometers away. We've never sent a probe into Neptune's atmosphere. We've never measured wind speed directly. Everything is inferred, calculated, reconstructed from images and spectra, and the careful analysis of how clouds move across the planet's face. And yet, from those fragments, we've built a picture of a world. We've learned that Neptune has weather more extreme than Jupiter's, driven by internal heat rather than sunlight. We've discovered storms that appear and vanish on timescales of years, defying the permanence we see on other planets. We've tracked wind patterns, measured temperatures, mapped the circulation of an atmosphere we'll never touch. That's the miracle of science, that you can understand something without experiencing it directly. That distance is not an insurmountable barrier to knowledge. That careful observation and thoughtful analysis can reveal truths about places no human will ever visit. But it also means our understanding is incomplete. There are questions we can't answer without better data, without more observations, without instruments we haven't built yet. Why do Neptune storms form? Where they do? What triggers their birth? What determines how long they last? How does the atmosphere respond to seasonal changes over Neptune's 165-year orbit? We have hypotheses, but not certainty. We have models, but not proof. And that brings me to something important. When we talk about Neptune's winds being the fastest in the solar system, we're making a claim based on limited data. We've measured winds on Jupiter, Saturn, Uranus, Neptune, the 4 giant planets. We've measured winds on Earth, obviously. We've even measured winds on Venus and Titan through careful analysis of atmospheric movements. But the solar system is larger than these few worlds. There are dozens of moons, hundreds of smaller bodies, entire regions we've barely explored. Somewhere out there might be winds faster than Neptune storms, more violent weather, more extreme. We say fastest in the solar system because it's the fastest we've measured so far. But so far is an important qualifier. It's a reminder that our knowledge is always provisional, always subject to revision when new data arrives. Neptune holds the record for now, but records are meant to be broken, and the universe is full of places we haven't looked yet. Still, even with those caveats, Neptune's winds are extraordinary. On a world that receives almost no energy from the sun, where temperatures are cold enough to freeze methane, where you'd expect stillness and silence, there is instead this relentless, furious motion. Winds that never sleep. Storms that grow and die and grow again. An atmosphere in constant turmoil, driven by heat from below, shaped by rotation, creating patterns we're only beginning to understand. It's beautiful. It's terrifying. It's a reminder that energy always finds a way to express itself, that heat always flows from hot to cold, that no place in the universe is truly still. Even at the edge of the solar system, 30 times farther from the sun than Earth on a planet where ice is hot, an atmosphere is an ocean, there's wind, there's weather, there's change, and that wind carries more than just gas and clouds. It carries information clues about Neptune's interior, about its history, about how worlds work when they're built a certain way and placed in a certain location. Every measurement we make, every storm we track, every wind speed we calculate, adds another piece to the puzzle. Slowly, patiently, across decades of observation, we're learning to read Neptune's atmosphere like a book written in the language of fluid dynamics and thermodynamics, in equations and images and the movements of clouds across a distant pale blue-green face. But there's more to Neptune than wind and weather, more than the storms that rage across its surface. Because time itself moves differently, they're stretched and compressed by distance and orbital mechanics into patterns that make a human lifetime seem impossibly brief, and a planetary year impossibly long. What if you could only celebrate one birthday in your entire lifetime? Not because life was short, but because the year was so impossibly long that even if you lived to be 80, you'd still be less than half a year old. One trip around the sun, one complete orbit. One full cycle of seasons each season, lasting longer than an entire human generation. That's life on Neptune. Time moves differently there. Not slower, not faster, but stretched into proportions that make our earth-bound sense of duration seem almost comically brief. A day passes in the blink of an eye. A year takes almost 2 centuries. And in that strange relationship between rotation and revolution, Neptune teaches us something profound about how we measure time and what time even means. Let's start with the day. Neptune rotates on its axis once every 16 hours and 6 minutes, about 2/3 as long as an Earth day. For such a massive planet, 17 times Earth's mass, nearly 4 times Earth's diameter, that's remarkably fast. The equator is moving at about 6,000 miles per hour just from the planet's rotation alone. Add that to the wind speeds we discussed earlier, and you get atmospheric velocities that seem almost impossible. But here's what's interesting. We didn't always know how long a Neptunian day was. When Voyager 2 flew past Neptune in 1989, scientists tried to measure the rotation period by tracking radio emissions from the planet's magnetosphere pulses of radiation that repeat each time the magnetic field rotates with the planet. They got a measurement 16 hours and 7 minutes. But later observations showed something puzzling. The radio pulse period seemed to vary slightly over time. Sometimes it was 16 hours and 6 minutes. Sometimes 16 hours and 8 minutes. What was happening was Neptune's rotation speeding up and slowing down. No, the planet's rotation is constant. What was changing was the radio emission pattern, which turns out to be influenced by Neptune's complex tilted magnetic field. The true rotation period, measured by tracking features in the deep atmosphere using careful Doppler measurements, is approximately 16 hours and 6 minutes. But it took years of observations and analysis to pin that down with confidence. It's a reminder that even something as seemingly straightforward as how long is a day can be surprisingly complicated when you're dealing with a world you can't visit, measuring things from billions of miles away. Now, let's talk about the year. Neptune's orbit around the Sun is enormous, about 2.8 billion miles in radius, nearly 30 times the distance between Earth and the Sun. At that distance, Neptune moves slowly, sedately, completing one full orbit every 164.8 Earth years. Think about what that means in human terms. Neptune was discovered on September 23, 1846. It didn't complete its first full orbit since discovery until July 2011, 165 years later. Every person who saw Neptune through a telescope in the 1800s died long before the planet returned to the spot in its orbit where it was first observed. Every scientist who calculated its position, every astronomer who tracked its motion through the stars, they lived and died within a fraction of one Neptunian year. If you were born on Neptune on the day it was discovered, you would have turned 1 year old in 2011. If you were born when Voyager 2 flew past in 1989, you wouldn't celebrate your first birthday until 2154. Your grandchildren might not even live to see it. It's a kind of immortality almost. A single Neptunian year outlasts empires, outlasts languages, outlasts entire eras of human civilization. During one orbit of Neptune, Earth makes 165 trips around the Sun. Generations are born, live, and die. Technology transforms. Everything changes except Neptune, which continues its slow, patient journey around the Sun, indifferent to the brief flickering of human time. Here's where it gets even stranger. Neptune has seasons. Like Earth, Neptune's axis is tilted relative to its orbital plane about 28 degrees, similar to Earth's 23.5-degree tilt. That tilt means different parts of the planet receive different amounts of sunlight as Neptune moves through its orbit. When the North Pole tilts toward the Sun, it's summer in Neptune's northern hemisphere and winter in the south. Half an orbit later, the situation reverses. But because Neptune's year is so long, each season lasts about 41 Earth years. 41 years of summer, 41 years of autumn, 41 years of winter, 41 years of spring. Imagine that. You could be born at the beginning of Neptune's summer and die of old age before autumn arrives. The seasons don't change on human timescales. They change on civilizational timescales. If Neptune had inhabitants, their concept of seasonal change would be passed down through oral history, through ancient texts, through records kept across generations. Our great-grandparents remembered when summer began. They said the clouds looked different then. Research shows that Neptune's atmosphere does respond to these seasons, though we've only been observing closely enough to see the changes since the 1990s. When a pole tilts toward the Sun, such as it is weak and distant, that hemisphere receives slightly more solar heating. The temperature increases by a few degrees Kelvin. Not much, but enough to affect atmospheric circulation, cloud formation, and the distribution of methane in the upper atmosphere. Here's a fascinating detail from the 2024 study that corrected Neptune's color. Scientists noticed that Uranus appears slightly greener during its solstices summer and winter, and slightly bluer during its equinoxes spring and autumn. The color change is subtle, but it's measurable, and it's caused by seasonal processes. During Uranus's summer, when the North Pole points toward the Sun for 42 years straight, methane in the polar atmosphere freezes and forms a hood of ice particles that thickens over time. These ice particles scatter light differently than methane gas does. They reflect more green and red light compared to blue, making the pole look slightly greener. When spring arrives and the Sun shifts toward the equator, the ice hood begins to thin and the planet's color becomes more uniformly blue-green again. Uranus takes 84 years to orbit the Sun, meaning each season lasts 21 years. That's a human generation per season. Scientists suggest that Neptune, with its similar tilt but longer year, likely experiences similar seasonal color shifts, but stretched over even longer time scales. We haven't observed long enough to see a full cycle yet. We're still in the early chapters of Neptune's seasonal story, still watching the slow unfold of processes that take longer than human lifetimes to complete. Think about the patience that requires, not just from the planet, which has no choice, but from the scientists studying it. Careers begin and end within fractions of a Neptunian season. Researchers hand off their observations to the next generation, who will hand them off, in turn building a record that might not pay off for another century. It's science's relay race as multi-generational project as act of faith, that someone in the future will care enough to continue the work. Let me ask you something. How does your sense of time change when you think on these scales? Does it make your own life feel brief, insignificant, like a mayfly dancing for a day in the eternal flow of planetary orbits? Or does it make your time feel precious, concentrated, a bright flash of consciousness in a universe that moves mostly in slow, patient circles? There's no wrong answer. Both are true. We are brief, we are also miraculous. The fact that we exist at all conscious curious, capable of understanding Neptune's orbit and calculating its seasons, is perhaps the most remarkable thing in the solar system. More remarkable than diamond rain, more remarkable than the 1,000-mile-per-hour winds. Because those are just physics, we are something else. We are the universe looking at itself, measuring itself, understanding itself across billions of miles and vast gulfs of time. And that's worth something, even if we only get to do it for a few dozen trips around the sun. Let's talk about orbital resonance, because it reveals another layer of Neptune's relationship with time. Neptune's orbit isn't isolated, it's gravitationally connected to other objects in the outer solar system, locked in mathematical patterns that have persisted for billions of years. Pluto, for instance, completes 2 orbits for every 3 orbits of Neptune, a 3-2 resonance that prevents the 2 bodies from ever getting too close to each other, even though their orbits technically cross. When Pluto is at its closest point to the Sun inside Neptune's orbit, Neptune is always somewhere else safely distant. They avoid each other through the clockwork precision of orbital mechanics, through a pattern established when the solar system was young and maintained ever since. There are thousands of other objects in the Kuiper Belt, the region beyond Neptune's orbit, that are similarly locked in resonance with Neptune. Some orbit twice for every 3 of Neptune's orbits. Some orbit once for every 2. Some have even stranger ratios, 5, 3, 7, 4 patterns that sound like musical intervals, like harmony written in gravity and time. These resonances shape the architecture of the outer solar system. Neptune acts like a shepherd, its gravity organizing the small distant objects around it into stable patterns, clearing out certain orbits and concentrating objects in others. It's been doing this for over 4 billion years, slowly sculpting the distribution of mass at the edge of the planetary system, creating order from chaos through nothing more than patient, relentless gravitational influence. Scientists suggest that Neptune may not have formed where it is now. Computer simulations of the early solar system indicate that the giant planets likely migrated, shifted their orbits over millions of years, as they exchange momentum with the countless smaller bodies that existed in the primordial solar system. Neptune might have started closer to the Sun and drifted outward, scattering debris, as it went eventually settling into its current orbit, about 2.8 billion miles from the Sun. If that's true, then Neptune's current orbital period, 164.8 years, is not what it's always been. Billions of years ago, Neptune might have had a shorter year, orbiting faster closer to the warmth of the young sun. The Neptune we see today is a refugee, a wanderer that found a stable home at the edge of everything and has stayed there ever since, its orbit barely perturbed by the faint tug of distant stars. There's a connection here to Hubble's long-term observations of Neptune, the outer planet atmosphere's legacy program, that has been monitoring Jupiter, Saturn, Uranus, and Neptune for over a decade. One of the program's surprising findings is that Neptune's cloud cover seems to vary with the Sun's 11-year activity cycle. When the Sun is more active, producing more ultraviolet radiation and solar wind, Neptune's upper atmosphere becomes hazier, cloudier. When solar activity decreases, the clouds thin out. This is strange. Neptune is so far from the sun that solar influence should be negligible. The amount of ultraviolet light reaching Neptune is minuscule compared to what Earth receives. And yet, Neptune's atmosphere responds. The correlation is too strong to be coincidence. Somehow, across 30 astronomical units of empty space, variations in solar activity affect Neptune's weather. Research shows that ultraviolet light can break apart methane molecules in Neptune's stratosphere, creating complex hydrocarbons that form haze particles. More UV means more photochemistry, more haze, more visible clouds. It's a subtle effect, but it's real, another reminder that even at the edge of the solar system, the sun's influence persists, shaping atmospheres and climates in ways we're still learning to understand. And this brings us back to time. The sun's 11-year cycle is short compared to Neptune's 165-year orbit. Neptune will experience about 15 complete solar cycles in a single year. Each cycle nudges the atmosphere, slightly creating small variations in cloud cover that accumulate over decades, over centuries, over the vast expanse of a Neptunian year. The planet's climate is shaped by the interplay of these different timescales: the 16-hour rotation, the 11-year solar cycle, the 41-year seasons, the 165-year orbit, all layered together, all contributing to the weather patterns we observe from our brief vantage point in time. Here's a thought experiment. Imagine you're an astronaut in orbit around Neptune. You're watching the planet rotate beneath you, watching the clouds race past at impossible speeds, watching day and night cycle every 16 hours. But you're also aware that the planet you're orbiting is moving slowly, ponderously through space, completing its orbit around a sun, so distant it looks like just another bright star. You're experiencing two kinds of time simultaneously: the fast, frenetic time of Neptune's day and the slow, patient time of Neptune's year. And both are real. Both are happening at once. Your sense of now contains both the immediate present clouds forming winds, blowing storms spinning, and the vast temporal arc of the orbit, a journey that began before you were born and will continue long after you're gone. That's the paradox of time on Neptune. Everything happens quickly and slowly at once. A day is brief, a year is eternal. And in between those extremes, life, if there were, life would have to find its rhythm, its pace, its way of making meaning in a world where the fundamental units of time are so different from what we know. On Earth, we measure our lives in years. We celebrate birthdays, mark anniversaries, track time by the cycles of seasons, and the revolution of our planet around the sun. On Neptune, you couldn't do that. A single year would outlast you by more than a century. You'd have to find other markers, other rhythms. Maybe you'd count days, almost 90,000 days in a Neptunian year. Maybe you'd count storms, cloud formations, the slow drift of the dark spots across the face of the planet. Maybe you'd give up on counting altogether and learn to live in the eternal present, where time is measured not by orbits, but by the pulse of wind and weather, by the endless motion of the atmosphere. But we're not on Neptune. We're here on Earth, where a year is a manageable 365 days, where seasons change in rhythms we can feel and anticipate. And from this vantage point, Neptune's timescales seem alien, incomprehensible, almost meaningless. What difference does it make that Neptune takes 165 years to orbit the sun? What does that tell us about anything that matters? Maybe that time is relative, not just in the Einstein sense, warped by gravity and motion, but in the experiential sense, that what seems like a long time to us is an instant to Neptune, and what seems like an instant to us might feel like forever, to something smaller, faster, living on a different scale entirely. That there's no universal clock, no objective measure of fast or slow. Only relationships, comparisons, the ratio between your lifetime and the cycles of the world you inhabit. Neptune teaches us humility. It reminds us that our perspective is one among countless others, that the universe contains timescales we'll never personally experience, processes that unfold too slowly for individual minds to grasp. But it also teaches us persistence, because even though we can't watch a full Neptunian year, we can begin the observation. We can record what we see, preserve the data, pass it on. We can be part of something larger than ourselves, a project that spans generations, a slow accumulation of knowledge that might someday in 2154 or 2319 or 2484 add up to a complete picture of how this distant, cold, magnificent world changes over time. So, where does this leave us? We've traveled from Neptune's discovery through mathematics, through the false colors of Voyager, through the science of spectroscopy and the strange physics of its interior. We've felt the fury of its winds, considered the brevity and eternity of its timescales. And through it all, we've been circling around a larger truth, that Neptune is not just a planet, it's a teacher. It teaches us to look again, to question inherited images, to trust careful measurement over dramatic pictures. It teaches us that distance is not a barrier to understanding, that light carries information across billions of miles, that mathematics and observation can reveal worlds we'll never touch. It teaches us patience, the patience to watch processes that unfold over decades, over lifetimes, over generations. And it teaches us perspective, because Neptune doesn't care about our sense of time, our measurements, our attempts to understand it. It spins and orbits and storms and rains diamonds in the dark, indifferent to our curiosity. But we care. We look, we measure, we calculate, we wonder. And in that act of attention, we become part of Neptune's story. Briefly, yes, but genuinely. But Neptune isn't alone out there in the cold darkness. It has companions, 14 moons that we know of, each with its own story, its own mysteries. And one of those moons is so strange, so utterly unlike anything else in the solar system, that it demands its own chapter in Neptune's tale. A moon that orbits backward. A moon that was captured, not born. A moon that's slowly dying, pulled inexorably toward a beautiful, terrible end. Imagine being captured, not metaphorically, actually seized by gravity, pulled from your orbit around the sun, forced into servitude around a planet that wasn't your home. Imagine spinning the wrong way, moving backward through space while everything else flows forward. And imagine knowing, if you could know, that your captivity has a timer, that every orbit brings you closer to an ending written in the mathematics of tides and gravity. An ending that will be spectacular and terrible and beautiful all at once. That's Triton, Neptune's largest moon. A prisoner, a rebel, and eventually, billions of years from now, a victim. This is a love story in a way, but not the kind that ends well. Neptune has 14 known moons, but most of them are small, irregular, barely worth mentioning, except as footnotes in astronomical catalogs. Triton is different. Triton is the 7th largest moon in the entire solar system, larger than Pluto, larger than Eris, larger than any dwarf planet. It's 1,080 miles in diameter, about 78% the size of Earth's moon. And it was discovered remarkably quickly after Neptune itself, just 17 days. On October 10, 1846, barely 2 weeks after Neptune's discovery, an English astronomer named William Lassell pointed his homemade telescope toward the newly found planet and spotted a faint point of light orbiting it. He wasn't sure at first the observation was difficult. The light was dim. Neptune itself was so faint that seeing anything near it required exceptional optics and patience. But he observed again and again, tracking the point of light as it moved, confirming that it was indeed a moon, the first satellite of the 8th planet to be identified. Lassell didn't name it immediately. For over a century, it was simply Neptune's satellite, or Neptune I. Not until 1949, when a second moon, Nereid, was discovered, did astronomers feel the need to give the first moon a proper name. They chose Triton after the Greek god of the sea sun, of Poseidon. Neptune, Poseidon, Triton mythology, organizing the cosmos, giving human names to alien worlds. But Triton is not like other large moons. It breaks a fundamental rule, one that most moons follow without exception. It orbits backward. In astronomy, we call this retrograde motion. Almost every moon in the solar system orbits in the same direction its planet rotates prograde motion. It's a natural consequence of how moons form. When a planet is young and surrounded by a disk of gas and dust material, and that disk is already rotating in a specific direction. Moons that form from that disk inherit the rotation. They orbit prograde forward in harmony with the planet's spin. But Triton doesn't. Triton orbits retrograde in the opposite direction to Neptune's rotation. It's as if the entire moon is moving backward through time, swimming upstream against the natural flow of the system. And that tells us something crucial: Triton didn't form alongside Neptune. It was captured. Scientists suggest that Triton originated in the Kuiper Belt, the distant region of icy bodies beyond Neptune's orbit, where objects like Pluto reside. Billions of years ago, Triton was one of those objects minding its own business, orbiting the sun peacefully. But at some point, perhaps 3.5 billion years ago, perhaps more recently, Triton passed too close to Neptune. The planet's gravity grabbed it, pulled it into an elliptical orbit, and gradually, over millions of years of tidal interactions, circularized that orbit into the nearly perfect circle we see today. The capture must have been violent. When a large object is pulled into a new orbit, energy has to go somewhere. In Triton's case, that energy went into heat-intense world-melting heat, generated by tidal forces as Neptune's gravity squeezed and stretched the moon's interior. Triton would have been geologically active, possibly molten, resurfacing itself completely and erasing any record of what it looked like before capture. What we see today is the aftermath. A moon that has settled into its new home, but still carries the mark of its violent past in its backward orbit. When Voyager 2 flew past Triton on August 25, 1989, the same day it made its closest approach to Neptune, it revealed a world unlike anything scientists expected. The surface temperature is around 38 Kelvin, which translates to about minus 391 degrees Fahrenheit. That makes Triton one of the coldest surfaces ever measured in the solar system, colder than Pluto, colder than the outer reaches of Saturn's moons, so cold that nitrogen freezes solid. And yet, despite that extreme cold, Triton is geologically active. Voyager photographed geysers, plumes of nitrogen gas erupting from beneath the surface, shooting up to 5 miles high, then drifting downwind and falling back as dark streaks across the pinkish ice. These weren't water geysers like those on Saturn's moon Enceladus. They were nitrogen geysers driven by a different process entirely. Research shows that sunlight, weak as it is at Neptune's distance, can penetrate a few feet into Triton's nitrogen ice. Beneath the surface, the ice warms just enough to sublimate, turning directly from solid to gas without melting. Pressure builds up under the translucent ice cap, and eventually it breaks through, releasing jets of nitrogen mixed with dark organic compounds. Complex carbon molecules that give the plumes their dark color. The wind in Triton's thin atmosphere carries these dark particles downwind, depositing them as streaks that can be dozens of miles long. It's weather, essentially. But weather powered not by heat from below, but by the faint, patient energy of sunlight absorbed slowly over months or years, until it reaches a threshold and releases explosively. It's a reminder that even in the coldest, most desolate places, energy finds a way to create motion change activity. Triton's surface is strange in other ways too. It's mostly frozen nitrogen, but mixed with methane, carbon dioxide, and water ice. The coloring is subtle pinkish in some areas, darker in others, with bright frost deposits near the poles. There are relatively few craters, which tells us the surface is young, geologically speaking, probably less than a few 100 million years old. Something has been resurfacing, Triton smoothing over the ancient impact scars, renewing the landscape. Scientists suggest this resurfacing comes from cryovolcanism, ice volcanoes that erupt liquid or slushy water mixed with ammonia, which acts as antifreeze, lowering the melting point and allowing the mixture to stay liquid in conditions where pure water would freeze instantly. These cryovolcanoes have created smooth plains, frozen lakes, features that look eerily like lava flows, but are made of materials that would be solid rock on Earth and liquid only in the extreme cold of the outer solar system. There's a region on Triton called Cantaloupe Terrain, a nickname given by Voyager scientists, because the surface looks dimpled and textured like the skin of a melon. It's unlike anything else in the solar system, a landscape of intersecting grooves and ridges that might have formed from upwelling warm ice or from stress fractures as Triton's orbit circularized and tidal heating varied over time. We don't fully understand it, but it's there undeniable a mystery written across hundreds of square miles of frozen nitrogen. And then there are the polar caps, bright regions of frozen nitrogen and methane that change with Triton's seasons. Because Triton is tidally locked to Neptune, always showing the same face to the planet, just as our moon does to Earth. And because Neptune's axis is tilted, Triton's poles experience extreme seasonal variations. For decades, one pole is in constant sunlight, while the other is in darkness. Then, the situation reverses. The bright frosts migrate from pole to pole, sublimating at one end, and condensing at the other, creating a slow, patient cycle of material transport across the moon's surface. It's a world that's alive in its way. Not biologically, but dynamically constantly changing, reshaping itself, responding to the faint tug of sunlight and the relentless pull of Neptune's gravity. But here's the tragedy. Triton is doomed. Because it orbits retrograde, because it's moving in the opposite direction to Neptune's rotation, tidal forces are acting differently than they do on prograde moons. On a moon like our own, moon-tidal interactions cause the moon to slowly move away from Earth a few centimeters per year, but measurable. The moon is stealing rotational energy from Earth, converting it into orbital energy, gradually spiraling outward. Triton is doing the opposite. It's stealing energy from Neptune, but because it's moving backward, that energy is being subtracted from its orbit, not added. Triton is slowly spiraling inward, getting closer to Neptune with every orbit. The rate is small, about 3.8 centimeters per year, roughly an inch and a half. At that speed, it would take billions of years to make a significant difference. And that's exactly what will happen. In approximately 6 billion years long, after the sun has swollen into a red giant and consumed the inner planets long after Earth has become uninhabitable, Triton will cross what's called the Roche limit. That's the distance at which tidal forces from Neptune become stronger than Triton's own gravity holding it together. At that point, Triton will be torn apart. Not suddenly, not explosively. Slowly, patiently, over perhaps thousands of years, Triton will stretch and fracture. Pieces will break off. Boulders will float away. The moon will become a ring, a vast, magnificent ring system around Neptune, far more extensive and spectacular than Saturn's rings made of ice and rock, and the shattered remains of what was once a world. And eventually, over millions of years more, that ring will dissipate. Some material will fall into Neptune's atmosphere, burning up in brief flashes of light. Some will be scattered outward, escaping into independent orbits around the sun. What was once Triton will be gone, dispersed, unmade, a world reduced to dust and memory. Does that make you feel anything? It makes me feel something, a kind of cosmic melancholy, a sadness for something that hasn't happened yet and won't happen for billions of years. Triton doesn't know it's dying. It has no consciousness, no fear, no awareness of its fate. And yet, the mathematics are clear. The ending is written. Every orbit is a step closer to dissolution. There's a question here about value, about meaning. Does it matter if a moon is destroyed billions of years from now? Does it matter if the destruction is beautiful, rings shining in the distant sunlight, a monument to what was? Or is there something unbearably sad about the idea that a world, This world with its geysers and its cantaloupe terrain, and its slow cycle of nitrogen frosts will someday cease to exist. Maybe what we're really feeling is recognition. Because we're mortal too, we're also moving toward an ending, though ours comes much faster. And maybe looking at Triton's slow spiral into Neptune's embrace reminds us that nothing lasts forever. Not moons, not planets, not stars, not us. Everything is temporary. Everything changes, everything ends, but temporary doesn't mean meaningless. Triton exists now. Right now at this moment, it's orbiting Neptune, erupting geysers, cycling nitrogen between its poles, carrying on the slow work of being a moon. And we, brief as we are, get to witness it. We get to point our telescopes and spacecraft at this distant captured world and say, "We see you. We understand a little what you are and where you came from. We know your fate even if you don't." That's not nothing. That's something. Let's talk about the other moons briefly because they tell a different story. Neptune has 13 other known moons, and most of them are tiny, irregular chunks of rock and ice, probably captured asteroids or fragments from ancient collisions. They orbit in chaotic paths, some prograde, some retrograde, none of them significant enough to have been given proper mythological names until recently. The second largest moon, Nereid, is particularly strange. It has one of the most eccentric orbits of any moon in the solar system, a long stretched ellipse that takes it from 840,000 miles away from Neptune, at its closest to over 6 million miles at its farthest. That's an enormous range, and it suggests that Nereid, like Triton, might be a captured object, something that was pulled into orbit but never fully settled into a circular path. Scientists suggest that when Triton was captured, its gravitational influence disrupted the orbits of any pre-existing moons around Neptune. Some were ejected entirely, some collided with each other or with Triton. Some, like Nereid, were perturbed into eccentric orbits that persist to this day. The Neptune system we see now is the aftermath of that ancient chaos, a configuration that reflects violence and capture, rather than the orderly formation from a protoplanetary disk. It's a reminder that planetary systems aren't always peaceful. They don't always follow the neat, predictable patterns we see in computer simulations. Sometimes there's catastrophe collision disruption. And the scars of those events persist for billions of years, written into the orbits and compositions of the objects that survive. Voyager also discovered 6 small inner moons during its flyby, tiny, irregularly shaped bodies, orbiting close to Neptune inside Triton's orbit. The largest of these Proteus is about 260 miles across, substantial, but still much smaller than Triton. Proteus is heavily cratered, dark, ancient, a relic from the early solar system that somehow avoided being destroyed during Triton's capture. These inner moons are shepherd moons, similar to those around Saturn. They help maintain the structure of Neptune's faint ring system, thin, dark rings discovered by Voyager made of dust, and small particles orbiting just above Neptune's cloud tops. The rings are named after scientists involved in Neptune's discovery: Gala, Leverrier, Lassell, Arago, Adams. Fitting perhaps that the people who found Neptune with mathematics are commemorated with rings made of material too small and dark to see without spacecraft. And then there are the outer irregular moons, 7 of them all discovered in the early 2000s using large ground-based telescopes. They're small, distant orbiting, far from Neptune in retrograde paths, likely captured Kuiper Belt objects that wandered too close and were pulled into Neptune's gravitational sphere of influence. We know almost nothing about them except their orbits. No spacecraft has photographed them. No detailed studies exist. Their names in a database, dots of light in telescopic images, mysteries waiting for future missions that may never come. But Triton remains the centerpiece, the most fascinating, the most tragic. It's the only large moon in the solar system orbiting retrograde. It's one of the few geologically active bodies in the outer solar system. It's the only moon we know of that's definitely spiraling toward destruction. And it's one of the most beautiful a world of subtle colors and strange landscapes of nitrogen geysers and frozen plains, of a surface renewed and refreshed by processes we're only beginning to understand. If we ever send another mission to Neptune, and there are proposals though, no funded missions yet, Triton would be the priority target, not Neptune itself, which we've already flown past, but Triton, which deserves closer study, longer observation instruments that can analyze the composition of those geysers and map the subsurface structure and measure the ice thickness and understand how such a cold world stays active. There's even speculation, cautious preliminary, but not entirely dismissible, that Triton might have a subsurface ocean. The tidal heating from its orbit combined with possible radioactive decay in its core might generate enough warmth to maintain liquid water beneath miles of ice. If so, that ocean could be habitable at least by microbial standards, a place where simple life might exist hidden in the dark using chemical energy instead of sunlight. It's a long shot. There's no evidence yet. But the possibility exists, and that alone makes Triton worth another look. Because if life could arise in an ocean beneath the ice of a captured moon, orbiting backward around the 8th planet, then life is truly tenacious, truly versatile, truly capable of finding a foothold in places we'd never think to look. So here's Triton, a world that doesn't belong, orbiting the wrong way, slowly dying, and yet somehow alive, active, changing erupting geysers into the thin nitrogen atmosphere of a place so cold that Earth's air would freeze solid in seconds. It's a reminder that the universe is full of exceptions, of things that don't fit the rules of stories, that don't follow the expected pattern. And maybe that's the real lesson. Not that Triton is doomed though it is, not that capture creates beauty though it does, but that even the outcasts, the prisoners, the things moving backward against the flow, they have worth. They have a story. They deserve attention. Triton was captured billions of years ago, pulled from freedom into servitude, its fate sealed by mathematics it has no capacity to understand. And yet it continues. It orbits. It erupts. It cycles nitrogen from pole to pole. It endures. And we, watching from billions of miles away, see in that endurance something recognizable, something almost noble. The refusal to stop, even when the ending is certain. The persistence of being, even when being is difficult. That's Triton. That's Neptune's great moon. A captive, a rebel, a dying world that hasn't stopped living yet. And as long as it orbits, as long as its geysers erupt, as long as nitrogen frosts migrate across its surface, it's still here, still real, still part of the dance of gravity and time that connects everything in the solar system, from the sun to the smallest speck of dust, all of us bound together by forces we're only just learning to name. We've journeyed through Neptune's past, through its false colors and corrected vision, through its interior and atmosphere, through its impossible timescales and its captured dying moon. All of this has been about seeing clearly, about stripping away assumption and inheritance, and looking at what's actually there. And now, we arrive at the end of that journey, at the place where all the threads come together, where the story of Neptune's new look becomes something larger than just a planet with the wrong color in old photographs. Let's come back to where we started. For 35 years, we thought Neptune was blue, deep, brilliant sapphire blue, a color that lived in our textbooks and our documentaries and our imaginations. And then in January 2024, someone looked again. Someone measured more carefully. Someone said, "Wait, that's not quite right." And everything changed. Not Neptune stayed exactly the same, spinning patiently at the edge of the solar system, indifferent to our misconceptions. What changed was us. Our vision, our willingness to question what we thought we knew. That's what this whole story has been about, really. Not just Neptune's color, though, that's where it started, but about the deeper truth underneath that. Seeing clearly is hard. That images can deceive, that sometimes the most trusted sources, NASA Voyager photographs from spacecraft, can be subtly, beautifully, persistently wrong. Not because anyone lied, but because translation is always imperfect and emphasis always distorts, and sometimes we enhance the truth so much that it stops being true. Think about what we've learned together tonight. We learned that Neptune was discovered not by looking, but by calculating, by trusting mathematics so completely that when the planet appeared exactly where the equation said it should be, it felt almost miraculous. Leverrier with his pen finding a world he'd never seen. Adams with his calculations coming to the same conclusion independently. Two minds separated by politics and pride arriving at the same truth through the universal language of gravity and motion. That discovery proves something profound, that the universe is knowable. That reality follows rules we can understand. That distance is not a barrier to comprehension, only to touch. You can understand something without ever visiting it. You can know a world you'll never walk on. And that knowledge is real as anything you can hold in your hand. Then came Voyager, 12 years of travel to reach Neptune, one brief flyby in August 1989, and images that took our breath away. The great dark spot, the white cirrus clouds, the winds racing at impossible speeds. And yes, the color that enhanced saturated impossibly blue color that became the defining feature of Neptune in popular imagination. But Voyager's images were processed for scientific visibility, not aesthetic accuracy. The blue was boosted to make clouds stand out to help researchers study atmospheric dynamics. And somehow, over decades, the explanation got lost. The enhanced images became the reality. We forgot we were looking at an interpretation, not the thing itself. Until 2024, when spectroscopy, the science of splitting light into its component wavelengths, finally gave us the tools to see Neptune's true color. Not deep blue, but pale greenish blue. Similar to Uranus, its near twin. Subtle, quiet, honest. The real Neptune stripped of enhancement revealed at last. And what did we learn from that correction? That beauty doesn't need exaggeration. That the truth, even when it's less dramatic, is always more valuable than the most gorgeous lie. That questioning inherited images isn't disrespectful. It's the highest form of respect, because it means you care enough to look closely, to measure carefully, to get it right. We went deeper, literally descending through Neptune's atmosphere into its strange interior. We learned that ice giant doesn't mean frozen. It means materials like water, methane, and ammonia compressed under pressures that turn them into something alien, something that barely resembles the familiar substances they started as. We learned about the mantle, that vast ocean larger than Earth, hot and dense, and possibly raining diamonds in the perpetual darkness beneath the clouds. Diamonds falling like snow through an ocean of compressed water and methane. It sounds like poetry, but it's physics carbon, crystallizing under extreme conditions, sinking slowly toward a core of rock and metal, creating beauty that no eye will ever see, wealth that has no value because it exists in a place forever beyond reach. That's the universe for you, full of wonders, most of them happening in places where wonder itself is impossible. And yet we know. We calculated it, modeled it, confirmed it in laboratory experiments that recreate Neptune's interior for a nanosecond at a time. Science gives us access to realities we'll never experience directly. That's its gift, its magic, its promise. We felt the fury of Neptune's winds, balled 300 miles per hour, the fastest in the solar system, driven not by sunlight, but by internal heat rising from the planet's formation billions of years ago. We watch storms appear and vanish, dark spots the size of Earth, materializing in the atmosphere, and then dissipating 5 years later, torn apart by wind shear as they drift toward the equator. Why does Neptune have such violent weather when it receives so little energy from the sun? Because energy doesn't always come from where you expect. Sometimes it comes from within, from heat trapped during formation, from the slow crystallization of materials settling through layers, from processes we're still working to understand completely. Neptune is restless, dynamic, alive in ways its twin Uranus is not. And that difference between two similar planets that behave so differently reminds us that small variations in initial conditions can lead to vastly different outcomes. A lesson that applies to planets, to lives, to everything that grows and changes over time. We stretched ourselves across timescales that dwarf human experience. A Neptunian day, 16 hours fast and frenetic. The planet spinning so quickly that winds get twisted into jets that race around the globe. A Neptunian year, 165. Earth years so long that if you were born when Neptune was discovered, you'd only be turning 2 years old now. Seasons lasting 41 years each. Patterns that unfold so slowly that watching them requires not just patience, but generational commitment. Scientists passing observations to their successors, building a record that might not pay off until 2154 or later. That kind of patience is humbling. It's a reminder that not everything happens on human timescales, that some truths reveal themselves only to those willing to wait to observe year after year, decade after decade, trusting that the pattern will eventually emerge if you just keep watching. And then Triton. Neptune's largest moon orbiting backward, a captured prisoner from the Kuiper Belt, slowly spiraling toward destruction. 3.5 billion years from now, Triton will cross the Roche limit and be torn apart by tidal forces, transformed from a world into a ring system, magnificent and temporary before dispersing entirely into dust and memory. There's something tragic about that fate, something beautiful too. The idea that even endings can be spectacular, that destruction can create its own kind of glory. Triton doesn't know it's dying. It has no consciousness, no fear. It just continues orbiting erupting geysers, cycling nitrogen between poles, doing the work of being a moon until the mathematics of gravity and time say no more. We're not so different, really. We're also temporary. We're also moving toward endings we can't prevent. But like Triton, we continue. We do the work of being human-looking, questioning, calculating, understanding for as long as we're given. And maybe that's enough. Maybe persistence in the face of inevitable ending is the closest thing to meaning the universe offers. So here we are at the end of this journey through Neptune's story. What have we really learned? We've learned that seeing clearly requires effort, that our first look is rarely our best look, that inherited images, no matter how trusted, should always be question-measured, verified. Neptune's false blue taught us that even science can perpetuate beautiful mistakes if we're not careful, if we let drama trump accuracy, if we forget to preserve the context that explains what we're actually seeing. We've learned that distance is not ignorance, that we can understand worlds we'll never visit, that mathematics and spectroscopy and patient observation can reveal truths across billions of miles of empty space. Leverrier proved that with his calculations. The 2024 color correction proved it again with spectroscopy. Every measurement, every model, every carefully constructed understanding of Neptune's interior or atmosphere or moons, they're all acts of reaching across the void and grasping something real. We've learned that time is relative, not just in the Einstein sense, but in the experiential sense that what seems eternal to us is a blink to Neptune, and what seems brief to us might be everything to something smaller, faster, living on a different scale. Our lives are short, yes, but they're also dense with meaning, with discovery, with moments of understanding that accumulate into something larger than ourselves. And we've learned that the universe is patient. It doesn't care if we get the color wrong for 35 years. It doesn't care if we argue about who discovered Neptune first, or if we take decades to understand its storms, or if we never send another spacecraft to study Triton up close. The universe just is spinning, storming, raining diamonds in the dark, following the same physical laws, whether we understand them or not. But we care. And that caring, that curiosity, that refusal to accept, we've always done it this way, or that's what the pictures show, that's what drives everything. Every correction, every new measurement, every willingness to look again and admit we were wrong. Science is not about being right the first time. It's about being willing to be wrong, to learn to adjust, to keep refining our vision until we see as clearly as our tools and methods allow. Neptune is pale greenish blue. That's the truth measured carefully confirmed across multiple instruments, corrected from decades of beautiful error. It's a quieter truth than the dramatic blue we inherited, but it's real. And real is always better than vivid, always more valuable than striking, always worth the effort it takes to see clearly. The planet hasn't changed. It's been there all along, 2.8 billion miles from the sun, spinning every 16 hours, completing its vast orbit every 165 years, indifferent to our attention. What changed is us, our instruments, our methods, our willingness to question. And that's the real story here. Not Neptune's color, but our capacity to correct ourselves, to say we got that wrong and now we know better. To improve, to refine, to see more clearly with each generation of technology and thought. That's what science is at its core, not a collection of facts, but a process, a way of engaging with reality that values truth over tradition, evidence over authority, careful measurement over inherited belief. If you take anything from this story, let it be this. Look again. Whatever you think you know about Neptune, about the universe, about yourself, look again. Question the inherited images, check the sources, measure carefully. Be willing to be wrong so you can learn to be right. Because the universe is full of things we've seen, but not truly looked at things we think we understand but have only glanced toward. And every time we look more carefully, with better instruments, better methods, better questions, we see something we missed before. Some detail, some nuance, some quiet truth that was always there, waiting for us to pay attention. Neptune waited 178 years for us to correct its color. How many other corrections are waiting? How many other false images, beautiful lies, comfortable misconceptions? We won't find them by assuming we already know. We'll find them by looking again, by measuring more carefully, by being willing to let go of what we thought was true when something truer reveals itself. That's the work. That's the journey. That's what it means to really see. And so, we leave Neptune as we found it, spinning at the edge of the solar system, pale blue-green, wrapped in storms, hiding an interior of impossible heat and pressure, orbited by a captured moon, slowly spiraling toward a spectacular end. It's still there, still real, still magnificent even without the enhanced color, even without the drama we once projected onto it. Maybe more magnificent now, actually. Because now we see it clearly. Now we see it as, it is not as we wished it to be, or thought it should be. And that clear sight is a kind of respect, a way of honoring the universe by refusing to distort it, by insisting on accuracy, even when accuracy is less immediately striking. Neptune doesn't need our enhancement. It never did. It's a world of diamond rain and 1,000-mile-per-hour winds and seasons that last longer than human lifetimes. It's a place where time moves differently, where storms appear and vanish, like thoughts where a moon orbits backward and geysers erupt into a nitrogen sky. It's already extraordinary. Adding false blue doesn't make it more so. It just makes it less true. So, here's to truth. Here's to looking again. Here's to the scientists who measured carefully, who corrected the record, who cared enough about accuracy to challenge an image everyone thought was settled. Here's to Leverrier and Adams and Galilei, who found Neptune with nothing but mathematics and faith in universal laws. Here's to Voyager, which gave us our first close look, even if that look needed later correction. Here's to Hubble and the Very Large Telescope, which gave us the tools to see truly. And here's to Neptune itself, patient, distant, real, still spinning, still storming, still there at the edge of everything we know, teaching us that the universe rewards careful observation, that truth is always worth the effort, that seeing clearly matters more than seeing dramatically. Thank you for staying with me through this long, quiet journey. Thank you for caring about a planet most people never think about, for being willing to dive deep into spectroscopy and orbital mechanics, and the subtle difference between greenish blue and deep blue. Thank you for valuing truth over spectacle, for being the kind of person who wants to see clearly, even when clear sight requires effort. The universe is vast and full of stories. Neptune's story of false colors and mathematical discovery of diamond rain and backward moons is just one among countless others, each waiting for someone curious enough to look patient enough, to measure brave enough to say, what we thought we knew might not be quite right. Let's look again. There are more stories coming, more worlds to explore, more misconceptions to correct, more quiet truths waiting to be found. If you'd like to join me for those journeys, I'll be here ready to drift into the next mystery, the next question, the next opportunity to see something clearly for the first time. Until then, rest well, dream gently, and when you wake, maybe look at something familiar, anything, a tree, a face, a photograph you've seen 1,000 times, and ask yourself, am I really seeing this? Or am I seeing what I expect to see, what I've always seen, what I was told to see? Because sometimes the most important discoveries don't happen out there in the distant darkness of the outer solar system. Sometimes they happen right here, in the moment when you question what you thought you knew and decide to look again. Sleep well, friend. Good night.